Oh yeah. What else to do? Got enough screens up there?
So the other interesting fact is that the first talk was just heard. He's a 9:15. His estimated arrival time is 9:10.
But he's in a car now.
Yeah, I texted him 10 minutes ago. It was still the same arrival time. So
Okay, that's good.
so Jake, so I'll just say just very few short words, just what we're doing. Maybe we'll how much time do you need? 5 minutes.
I was primarily going to say make remarks and then I'll take questions if Chris shows up.
I see. Okay. Okay. Perfect.
Do you want a live mic? A live would probably be better.
That was like with university presidents.
Well, there's no similar. So I worked with Oscar.
Yes. Talk before you. Thank you so much. Jake, I think I'll start. I'll just say a few words and I'll actually one
Yeah, go ahead.
Okay, hello? Let's see. So, welcome to our two-day workshop on noisy intermediate-scale quantum systems, and thanks to all of you for being here. So, my name is Alexei Gorshkov, and of course, the reason we're having this workshop is because it's a very exciting time to do quantum research these days, because experimentally available quantum systems are approaching the state where they might be able to answer some interesting questions that we might not be able to answer classically. And all of this despite the fact that these systems are somewhat noisy and intermediate scale on the order of 100 qubits. And that's why sort of John Preskill coined this term NISQ, noisy intermediate scale quantum systems. We have an exciting slate of speakers, both theorists and experimentalists, including John, who's of course a theorist. And we're hoping that the talks and the discussions will generate sort of new exciting ideas. So before we start, I would like to thank Arthi Sundaram and Goran Alagic, who actually did most of the work in organizing this workshop, as well as TQC that we had for the past 3 days. Our first speaker will be Chris Monroe, and let's see, did his title change from the... Quantum computing with atoms. Chris, ready? Okay, thanks, Chris.
Thanks, Alexei, and Jake. Thanks for having me here. Happy to kick off this two-day workshop on near-term quantum devices. And I guess I'll say at the outset, we'll hear today and tomorrow a selection of presentations from both experimental and theoretical perspectives. On the experimental side, there are a few technologies that are sticking out now, and I would say in atomic physics, using atoms as qubits, I suppose we haven't really, well, I don't want to speak for everybody, but I haven't really thought that the term NISQ is super remarkable, because in atomic physics, we don't really take error correction very seriously yet, because we don't need to. The passive errors in atomic systems can be very, very low. Maybe not low enough, we don't know yet, but I'm pretty sure that we can get pretty wide and deep circuits, certainly well beyond quantum supremacy, where you can't simulate the behavior of the system on any classical computer. And I would say not unlikely, even without error correction, to be able to hit applications that are actually useful. We'll see how that goes, of course. So we've been thinking about this for a long time, how to string together gates with passive, you can call it passive error correction, just designing your system right. And this is an illustration of that, where the qubits here are each individual atoms, all of the same isotope of the same element, so they're perfectly replicable. A lot of this technology comes from atomic clockwork, certainly where I got my start in this field. Because they're replicable, in a sense, they have the first requirement for scalability. Well, they're replicable. You don't have to worry about inhomogeneities. When these qubits are left alone, the idle errors, I won't say they're zero, but they're as low as we'll ever need them to be. If they need to be 10 to the minus 6, the idle errors, we can do that. They're atomic clocks. We can get them by some measure replicable and good down to 10 to the minus 18. We don't need, fortunately, we don't need to get anywhere near that. So that's the one. Right there is a couple of recipes for scaling, is that you have replicability, and that as you make the system big, you don't have to worry about the idle qubits, because they're not going to lose coherence. We don't really speak in terms of T1 and T2 in atomic systems, because they're as long as you need them to be. So it comes down to, and this is sort of interesting, it comes down to, it sounds like a cliche, but it comes down to engineering. The entirety of our error budget we understand, to maybe a part per million. We understand the errors, and they all have to do with the control system, every one of them. And in this case, for trapped ions, the control system starts with the trap itself, which are a bunch of electrodes that hold voltages, and they have to be controlled pretty well. But we understand how that's going to scale in the near term and over the next 10 years or so, because they have nothing to do with quantum physics. The other controls will be, in this case, in this particular case of atomic ions, we use laser beams to affect quantum gates and entanglement, and also other lasers to measure and initialize the system. I'll talk a little bit about that and hopefully branch out into a few of the small applications that we've demonstrated. So I'll talk on behalf of both my research group at the University of Maryland, but also just down the road from here, the startup INQ, which is developing commercial ion-trapped quantum computers. Okay, so I won't spend much time on this slide. In fact, it's somewhat outdated, even though it's only a few years old. This is extracted from a review in Science of a few of the technologies that are starting to spin up. They're looking like we can maybe build small systems out of these technologies from atoms and superconductors in particular. We'll hear a lot about that today and tomorrow. Within atomic physics, I already hinted that we have these atoms behaving as individual qubits. The qubits themselves are actually atomic clock levels. So we pick pairs of levels in an atom that, in this case, these are the ground state levels in the ytterbium-171 isotope, which is remarkably simple. The quantum numbers of the low-lying energy levels are exactly that of hydrogen. So we have a pair of levels that have very small magnetic field shifts because they're m=0 states. So we get a lot of passive control that way. And the energy splitting is Planck's constant times this 12.6 gigahertz. That's the atomic clock. I could write it out to a few more digits if I wanted. So this is where we store our information in terms of qubits, and we can measure, in all atomic systems, we measure the qubit and initialize through dissipative optical pumping or fluorescence techniques. And they're very good. They're as good as you need to be. Measurement per qubit can be more than 4 nines, and there are ways to get it even more than that. But again, if you don't have 10,000 qubits, you probably don't need 4 nines. So you keep all the number of nines at bay, and of course work on the lowest one. The control of the qubit is somewhat interesting, and here's where we start to branch into engineering. Now, I've been inside lasers my whole life, and I'm happy to say that the control laser of ytterbium-171, we don't go inside that laser because it's at a wavelength that is industrial. 355 nanometers is, in a sense, the optimum wavelength to think about controlling coherently these qubits, and this laser is produced for the lithography industry, for making CMOS masks and so forth. So it's made very well. It's research quality, but I wouldn't call it a research laser. It's fixed frequency, and that suits us just fine. And there's the only adjustment. It's the on button, I like to say. And so it's part of the system, and it works for years. You just buy it, and you can buy as much power as you want. I won't get into too many details. This is actually a pulse laser, so it produces a spectrum, which is a frequency comb, and that's really important because it allows us through a 2-photon transition to bridge the qubit and do control operations. But the laser itself is very passively stable. We stabilize it further, of course, but right out of the box, it's very good. Okay, so I'm going to talk a little bit about how we wire up these individual atomic ions. It is by, it's arguably the cleanest system right now in terms of control. We know how to generate entanglement over medium-sized systems, and I'll comment on that. So briefly, I'll talk a little bit about the circuit model. Of course, all this is pre-error correction because the fidelities can be very, very good. So I'll tell you how we generate entangling gates, 2-qubit entangling gates. Now, this is a little bit of a hand-waving argument. In some regimes, it's actually accurate. In others, there's some more details that I'll cover in due time. The idea here is if you have a line of atoms, and by the way, they're separated by several microns. We can obviously resolve them optically because the wavelength is much smaller than that. If we want to entangle any pair of these qubits, we can apply optical tweezer forces on that pair. And we do it in such a way with the laser that the selection rules give us a qubit state-dependent force. And for simplicity, I'll assume this force is transverse to the chain. For technical reasons, this is really what we want to do. These are the stiff modes. They're high frequency. They're lower noise. They're easier to control. And when we tune this laser just right, if we use spin up and spin down qubit language, and in this drawing, spin up receives a kick upward and spin down receives a kick downward, then you can see that depending on the state of these 2 qubits, the Coulomb interaction will be modulated. If they're both spin up, they will move up together, and their Coulomb interaction is the same as it was. Same with spin if they're both down. But if they're in opposite spin states, they're a little further apart, and the energy defect, if you assume this little displacement is tiny compared to the separation, and it's nanometers typically, then you can expand this defect and you get an effective 1 over r cubed type interaction. And then when you write down the 4 possibilities of these 2 qubits, you see that there's a nonlinear phase shift, because when you had mixed states of spin, you get the same energy defect. And this, when that phase is set to pi over 2, is as powerful, expressive as a controlled NOT gate. So it can form part of the universal logic family. Okay, a few more details now. And this actually is accurate physics if this force is applied really fast. If you do it super fast and then you return the atoms much faster than any of the normal mode frequencies, which are, by the way, a few megahertz. So as long as you're really fast compared to megahertz, the physics is accurate. We're not faster than a megahertz. We're actually a little bit slower than a megahertz. So in fact, there are normal modes of motion you have to deal with. This is a very interesting thing. This is really classical physics. And again, I don't have time to discuss too much, but we can apply laser pulses and shape them using classical techniques to pre-calculate the pulses so that all these normal modes cancel at the end of the gate. So it's as though we did it in this ultra-fast regime. The trick is you're adding classical complexity, but again, I don't want to trivialize it, it's engineering. There's nothing quantum about modulating a laser in just the right way to apply the force the way you want. The good news is when you do that, you're coupling to all these normal modes, and these normal modes are non-local. You don't have a 1 over r cubed fall off anymore. In fact, it's infinite range. So as long as you can deal with all these normal modes, you have an all-to-all connectivity. And this is incredibly efficient when it comes time to taking a real problem and compiling the gates to realize an algorithm. The gate count actually can shrink instead of blowing up if you had a nearest neighbor graph. The other sleight of hand is that we don't do this gate in the z basis. The spin-dependent force is actually in the x basis. It's sort of a detail. Sometimes it's called a Mulmer gate. It's based on physics discussed a long time ago by Serac and Zoller in a different regime. Sort of the same idea. You're modulating the Coulomb interaction between ions to make entanglement. So this is the native operation that pretty much all ion trap systems use. It's an XX gate. Sometimes we call it an icing gate, but it's as expressive as a controlled NOT gate. And the typical times for these gates, I said they're slower than a megahertz, so the typical times are tens or maybe even longer, microseconds. The fidelities, again, right off the bat, it's not hard to get in the high 90%, but the important thing is even at 98%, that 2%, we know where that noise is, and it's not fundamental. It's not a T2 process. It's always induced noise from the laser beam that's controlling the system. So we sort of know what the error budget is. Okay. So with that, we have built several systems, both at the university and also at INQ, to execute algorithms, small algorithms on small systems. And it's actually become a little bit of a user facility in a certain sense over the last several years. And these are I think all of these are from the university only over the last many years. And what's interesting is people from all walks have come to us wanting to run circuits. Admittedly, they're small circuits. At the university, we're limited to under 10 qubits right now. And we've been running things, and it's almost like going to school again. A lot of condensed matter physics behind these. But also, Jake mentioned metrics and benchmarks. We're running small algorithms that are sort of useless on their own, these oracle algorithms like Bernstein-Vazirani, but they're really useful for testing the overall fidelity of a system. It's just a single metric. Did it work or not? It's just a binary value, but it tells you something about the connectivity of the system and the fidelities of the aggregate system. Again, I don't have time to talk about many of these. In fact, I'm probably running out of time already. I'm going to skip this one, a circuit on testing whether unitaries scramble or not. There's a recent paper that describes this. But I want to move on to, very recently we've been thinking about dynamical circuits. That is, circuits that we can use classical feedback to optimize in a certain way. And this is finding a lot of use in many different types of algorithms. Some people use the term machine learning here. In this case, the machine learning is really on the classical side, where you somehow optimize the classical parameters and all the gates for a circuit to do something, maybe to make a state or to optimize some function, to minimize a cost function. In this case, again, lower your sights. This is a 4-qubit a 4-qubit system where we're trying to make just a particular quantum state. With 4 qubits, there are 16 basis states, and we want to make this particular superposition equally weighted, 1/6 population each. Sometimes it makes connections to bars and stripes in terms of images, but again, there's only 4 pixels here. But these 6 states selected have symmetry. They either have bars or stripes in them. And the question is, how do you make that state? It's actually not obvious how to make it using gates. If you write down the quantum states, it's pretty complicated. And of course, if you make this a 3x3 or a 4x4, it gets even more so. So with our 4 qubits, they're fully connected. We applied gates in a certain pattern where each one of these boxes has a classical parameter. And this is one layer, say, of a fully connected system. And we're using all 6 2-qubit gates here. We can also simulate, well, not simulate, run different connectivities. So in this connectivity graph, we're missing some entangling gates. We might expect this layer of a circuit is probably not enough, at least in a single instance, to make this state. And we do, that's borne out in the data. We need to apply that one twice to make an arbitrary state. And again, the idea here is to, with our ions, to make some measurement. This is the target state. Derive some figure of merit, some overlap, some variance, some separation between the 2 distributions if you want, and then go to the classical computer and try to optimize 20 or 30 parameters. Very difficult to do that, even with 4 qubits. And then apply this standard circuit with different parameters and go back and forth. So this is sort of a loop. We're finding this a lot in variational quantum eigensolvers, quantum approximate optimization algorithms, and so forth. And very, very quickly, the classical optimizers can actually limit the whole system, even with 4 qubits. In this particular classical optimization called particle swarm, it's not so efficient because we're randomly picking out places in the phase space of all these parameters. And after many iterations, this is not the number of layers. This is the number of iterations in a given number of layers. I think these are all, oh, here we go. A here is 1 layer of full connectivity. This is 1 layer of reduced connectivity. This is 2 layers of reduced connectivity. And the range here has to do with the sampling of the particle swarm. There's some error bars in theory. And the experiment in blue, we see that if we have reduced connectivity with only 1 layer, as I promised, we're not going to get down to the 0. By the way, this figure of merit, you want it to be 0, the sort of the distance between the 2 states. And it starts to make it, with 2 layers of this reduced connectivity, we expect it to start to converge, but it's just super slow because this optimizer is, I think there's 26 parameters in this fit. Very hard to do that. It turned out a Bayesian classical optimizer worked a lot better. Maybe not a surprise for those of you that are actually professionals in optimization. And in this case, the experiment in theory, there's no error bar on the theory because there's no distribution of trial states to begin with. And you'll notice after only a few hundred instead of more than 1,000, we do converge into the correct state. So you can sort of see the distribution of the final states is very close to what we expected. Again, kind of a toy model, but to me what's neat is that we're now adapting a quantum circuit using optimization of the classical parameters that drive that circuit. Seems to be a theme in a lot. A more recent experiment, we've used techniques from QAOA with a few more qubits to create states, interesting states, subject to this Hamiltonian, which is a transverse Ising model with nearest neighbor connectivity in a ring. Here's sort of a circuit you might apply. So here in QAOA fashion, we apply the first part of the Hamiltonian and then the second part. The field part are just rotations. And we have sort of a ring of nearest neighbor identical Ising operations. So there's actually only 2 angles in this because these are all identical. If we, at the critical value of g equals 1, there's this phase transition. And at the critical value, the ground state, in a sense, is the most interesting. We use QAOA techniques to find that ground state. We expect theoretically that with 3 layers of this circuit, we should be able to get the exact ground state. And this is sort of data with 1 and 2 layers of this circuit here. Again, minus 8.8 is down, all the way down to the bottom here. We didn't quite make it with p equals 1 as expected. P equals 2 is a little worse. So this is telling you that that even with 7 qubits, and I promised the gates were so good and so forth, even with 7 qubits, we're seeing that things get a little worse as we add layers. So we didn't even do p equals 3 in this case. By the way, this is in collaboration with Tim Say at Perimeter and Sonik Ajori at Intel. We use the same type of a circuit to make another type of a state that I just learned about not too long ago called the thermal field double state, and under the same Hamiltonian. The thermal field double state is a partitioned system that is just a straightforward thermal state when you trace over either system and look at the other. But it's a pure state overall between the two systems, and it has these Boltzmann factors according to the eigenstates. So it's like a thermal state. It's sort of like a bell pair extended to thermal states under some spectrum of Hamiltonian. In this case, it would be an interesting Hamiltonian, the transverse field Ising model here. And in this case, again, this will appear on the archive very soon. In this case, each layer of the circuit actually has 4 terms. To realize this, I'm not getting into too many details, and I'll probably skip across this. This state, by the way, is motivated in black hole physics, thermal states. And when you have one that's hidden in a black hole and you have another one outside, if you want to think of the whole system as a pure state, this is one model of that. Making that entangled state, especially under a complex Hamiltonian, is pretty tricky. Again, sorry, I'm kind of running out of time here. Now going over to INQ and talking about benchmarks, I hinted that we're playing around with these Oracle algorithms, Bernstein-Vazirani. There's a hidden string, and in a single query, you should be able to find it with perfect efficiency. And so this is a 11 qubit circuit. One's an ancilla, and here we're hiding a 10-bit string with the pattern of gates here. You can clearly see what the string is, 1101, 011, 001. And in a single query, of course, you should ideally be able to pick out that state in this measurement scheme. And this is all 1024 circuits, and these are the success rates. And again, each Ising gate is let's see, each Ising gate is, in this case, I think it was like 98.5%. So the error sort of makes sense with this aggregate error at the end. And again, this algorithm is not useful on its own, of course, even when you scale it up, but it's very useful as a very simple metric to how well your system's doing. Now you'll see this is a little bit of a trivial circuit. You don't need full connectivity here. You do need every qubit connected to the ancilla, but we can, of course, make the ancilla any qubit we want. So I'm not showing all the data, but there are actually I guess 10 times 1024 circuits. There's 10,000 unique circuits here. And with that, you can test all the connections. So it's a very useful benchmark, and we'll continue hitting this algorithm as we grow our system. The hidden shift is another version of that. This was first suggested to us by Martin Rottler at Microsoft, and we did a smaller version at the university. It's a little more complex circuit, depending on the function that you're hiding the shift in. It does require a non-trivial connectivity. It also classically requires exponentially more queries to find out what that hidden shift is. Now, at INQ, we've also been playing around with variational quantum eigensolvers in the molecular chemistry realm that a lot of the community is looking at. And these are theoretical, this is a theoretical table on how many qubits and how many gates you need to simulate the ground state of the water molecule using a standard VQE approach. And I'm shifting so we know the answer in water, it's minus 75 something Hartrees. And when we offset from that known answer with a deeper circuit in the VQE algorithm, we converge after maybe about 12 or 15 qubits. And you can see several hundred circuits, several hundred gates, we should be able to converge to the answer in H2O. Now, what's interesting about these first two columns is that the number of gates here is sort of the naive application of VQE. And without any approximation, given, and this assumes full connectivity, by the way. If you don't have full connectivity, that number will probably grow, especially as the system grows, maybe by the square root of the number of qubits you have. But in our system, we have full connectivity, and furthermore, we were able to compress it by about a factor of 5 because of the expression of our gates. And this is work Yongqing Nam at INQ, and also Ken Brown at Duke really had a big hand in the Jungsang Kim as well. So this is all doable on current technology. Admittedly, we're just starting our march down there, but what's notable here is that the error bars, both systematic and statistical, are not so much different than the so-called chemical accuracy. This is basically KT. That's what you need to hit. And as we go deeper in the circuits, it's still small. We're pretty confident that we should be able to go all the way down here. Okay, so I'll also note that other molecules that have been simulated, after 2 iterations, they blow up. So things are not converging in these other technologies because the gates aren't as good and the connection is not as good in those systems. Okay, so I want to briefly talk about another type of quantum computer that we have in trapped ions that is actually a little easier in terms of engineering. Sometimes we call it analog quantum simulation. Instead of doing a pointwise icing gate between pairs, we can, of course, apply a fully connected icing chain by having a big fat beam. It's a lot easier because now we don't have to focus any laser beams. And beam fluctuations are much easier to deal with here. And we end up with a Hamiltonian, not surprisingly. It turns out to be an all-on-all icing coupling. This is an approximation, but it's a long-range coupling where it's an inverse power law where alpha varies between all-on-all, 0, and dipolar, 3. And I'd say Alexei Gorshkov, our chair, is sort of a world's expert in these long-range icing systems, and he's helped us understand some of the interesting phases that happen when you have such a power law interaction. We can add a transverse field, and to give you a sense of scale, there are no phonon operators in here because we're in the dispersive limit where we're far detuned, and so we can safely ignore, we can adiabatically eliminate these phonons. The price we pay is that the couplings are slower yet. So instead of tens of kilohertz, it's about 1 kilohertz or so at best for nearest neighbor. And again, there's been a flurry of activity doing simulations with these magnetic systems. I won't get into many of these details, but with global beams, we have the opportunity to increase the number of qubits without super serious engineering yet. So at the university, we've pushed things to many dozens of qubits, up to 50 plus or so in a variety of applications. And since I talked about QAOA before, we have 2 separate experiments on campus. One is room temperature, one is cryogenic at 4 Kelvin that allows us to hold 100 plus spins. And the idea here is to, with our long-range icing, transverse icing model, prepare the ground state of this thing. And hopefully you're near criticality. And what critical means here is it's not B is equal to J naught because we have this long range, but we can sort of simulate where the critical parameters are in this Hamiltonian, and that ground state's interesting. Very small gaps, and there's high degeneracies and frustration and so forth. So here the idea, like before, is to apply these global layers. And what's nice here is that each layer only has 1 parameter now. We don't have to worry about all the individual gates. So in a sense, the classical side here is a little easier. And we're going to alternate between these non-commuting parts of the Hamiltonian, and hopefully, with enough alternations, we can realize a pretty good replica of the ground state. Now, in the systems we're dealing with, we can do a lot of theory and understand what the spectrum is, and so our figure of merit here would be, this is a little tricky. This is the energy we get under these classical parameters divided by the bandwidth of the whole energy spectrum. So when eta is equal to 1, that means we've hit the ground state. When it's equal to 0, I guess that means we've hit the excited state. We went the wrong way. So 1 is good, 0 is bad. And when we start with a certain guess, in this case, we start with them all prepared in the X state. After a few iterations of, I think this is all, I think, just 1 layer. But after iterations of optimizing the parameters that go in there, it comes close, not to 1, but something that's a little below that. Again, theoretically, we understand what this error between whatever it is, 0.98 and 1, has to do with the fact that QAO is approximate, it's the A. It won't get you the perfect ground state. And of course, it's a smooth landscape when we look at just these 2 parameters in a single iteration. There's just 1 angle associated with that term, 1 angle associated with that term. And if we start in some place, we can use a gradient descent, simple gradient descent classical algorithm to define the ground state. And that's mapped right there. So I guess I'm going to step out a little bit and speculate on how we're going to scale the system. You might be disappointed that we're only doing circuits with on the order of 10, pretty soon about 20 qubits, and even our global operations are less than 100. I mean, those will certainly change. And I hinted at one of our systems, it's cryogenic, and we can load many more than 100 ions in there, and they stay there pretty much all day. And it's because we're not going cold to go cold. We're going cold to lower the pressure. So it's just cryo pumping at 4K. As a closed cycle system, it's actually not super painful. This picture is kind of fun because there is an impurity in here. It's probably a different isotope of ytterbium, or maybe it's in the F state, it's dark. But that gap stayed in the same position all day. That means there was not a single reordering collision in the system. So we're pretty comfortable with dealing with a few hundred qubits in the system. The real problem with scaling, you might argue, when you look at an AMO lab is this. And I see Dave Hayes in the audience. I don't know if you're in here. Maybe you're on the other side. But so this is actually an experiment I didn't talk about. It has 2 ion traps where we're doing photonic protocols to communicate and teleport information in this modular type of approach. But the fixed cost is enormous in lasers and the control of the system. And I mentioned that's the challenge. It's all about control. And this is a challenge. Well, over the last many years at the university, we've, without too much of an exaggeration, we've put everything you see here in this box. It's a little bit of an exaggeration. We didn't put the students in there for sure. But, the control lasers, the CW lasers are fiber fed. Those are almost afterthoughts. But the control laser and all the coherent stuff, all the important stuff is in this meter cube box. And this has been afforded through a big IARPA project that actually aims to error correct qubits, strangely enough. But to error correct qubits, according to a simple Bacon-Shor code, we need very high performance on the individual gates. And to get very high performance, we really had to start thinking about a system, not physics. So there's a lot of engineering that goes in here, and this is helped by Sandia that provides the chip. This is a drawer full of 6 CW tunable locked lasers, all fiber delivered. It's in a drawer. This is from AO Sense. Cold Quanta is producing not the vacuum chamber we have in here, but more experimental vacuum chambers that can be cryogenically cooled, and they're very small. So we're sort of applying this industrial approach to the individual components, and we're just integrating in the end. Coherence provides this laser I mentioned, the 355 laser, and I list them because we actually had to modify it. I lied, we had to get in that laser just to make a modification because they wouldn't do it at the factory, but they showed us how to do it. They lent us tools. So we now know how to do this to get increased phase stability in that laser. So this is a real system, and it's starting to produce, so you'll hear a lot more about this in the coming months and years. At INQ, we developed technology basically based on this footprint. This is a picture of System 1, which has actually now been retired. At INQ, there are 3 fourth systems on the way. And again, this is the picture I showed at the outset. It uses the same Sandia chip. And so to scale, you might still ask, well, how are you going to get beyond a dozen or so? Well, I didn't mention these individual beams that poke atoms. They sort of saturate at 32. And that has to do with the fact that our modulator only has 32 channels. We could increase that if we wanted. I don't think we're going to need to or want to because we have such a very fancy software package that we can move atoms around and scale this way. And this is illustrated actually when we load. At INQ, we have an automatic loading procedure. Type in a number, how many ions you want, and there they are. They're with maybe a 75% probability. Each try loads an ion in the slot, and it gets shuttled over. They're zigzag, they get pulled out, we focus in, and we're ready to go. All in about a minute, and then we can take data on the system. Again, we only have 32 laser beams, and one way to scale, and this will sound sort of retro, but we know that we can put several hundred ions in a line. And even though we only have 32 laser beams, we can move the ions like a tape moving across a head. Now you might ask, when you have several hundred ions in a line, the normal modes are a mess. But one thing we're learning, this is a little bit of a surprise, is that even though we couple these normal modes, there's an emergent modularity that happens. And it turns out that we only have to deal with each ion and its maybe plus or minus 10 or 20 neighbors. So we abandon full connectivity, but we get to scale. So we can do gate, it's not shown in this way, but we can do gates over here and here at the same time, and they don't interfere. In fact, the crosstalk falls off like distance cubed. So as long as you are able to admit a tiny bit of error, You don't have, it's not a problem dealing with this long-range Coulomb interaction. That's really important. I think it'll get us to many hundreds of qubits using current technology. Now, in the long run, I didn't talk about it at all. This is a sort of a concept picture. Once we can make modules, we can also go off chip using photonics to truly scale to hundreds, thousands, or even more. If you can stamp out these red boxes and get an efficient photonic connection, that's really the bottleneck. All of this stuff's classical. It exists. Optical cross-connect switches, beam splitters, and so forth, and eventually they'll be put on chip with waveguides and so forth. So our path to scalability, I would say we have the requirements, we have the initial sort of the demonstrations. It really comes down to just executing. And I borrowed this slide, you've probably seen it, from Hart McNevin at Google, the famous number of qubits, number of gates, or if you want, 1 minus 1 over fidelity or something like that. And as we scale, of course, we need to move up and to the right. Everybody wants to be up and to the right. It's not hard to move up. Sorry, it's not hard to move up and to the left. You can throw 1 million qubits together, but you can't do anything with them. That's not very interesting. And in ions, we can put 2 ions together and do 3 nines, or probably 4 nines, 5 nines. But with just 2, it's not so interesting. You really need to go up in this direction, and I think these black dots are sort of a range of different approaches with ions. These are not computers, but global simulators. We really think that in the coming years we're going to clearly punch through this supremacy border and hopefully hit some treasure along the way before we have to do error correction, which may be when we have 200 or 300 qubits. Okay, well that's all I had to say, and again, a long list. A lot of these folks are in the room, and you'll notice a lot of them have gone over to industry. Even some of them somehow went to Honeywell. It's just, it's crazy. And this is a group at INQ. Many of them are here as well. Thanks for your attention.
Thank you, Chris, for an exciting talk and for being super on time. We have plenty of time for questions. John?
Could you say a little more about this emergent modularity of the normal modes? It sounds wrong.
Emergent is one of those terms that usually means you don't know what you're talking about when you say emergence, usually in the context of condensed matter. Well, so the basic idea in any number of qubits that we have is that and you should picture a bunch of pendulums connected by springs. When you have 1,000 of them, it's sort of a mess. If you wiggle one of them, forget it. So the information is lost to a classical thermal environment. But we wiggle these pendulums in a very special way. And when we hit 2 of them, we pulse shape the laser. And with up to maybe 100 qubits, we can actually do all the classical physics and take care of all the normal modes on your laptop. And it turns out each of the normal modes is excited. And at the end of the gate, we want it to be de-excited so that the normal modes are no longer entangled with the spins. Well, we've learned that by simplifying the laser pulses dramatically, maybe with only 10 control parameters instead of 100, we get within a whisker of perfect fidelity anyway. And we also see that when we look at the phonon wave functions, they're local. I should say an emergent locality or something. I mean, that sounds too fancy. But it was a little bit of a surprise. We thought this was a fundamental scaling problem. We can't put too many ions in one chain because then the information leaks. No. The phonons are phase coherent, and they can sort of interfere at the boundaries. So I didn't mean to make it sound more fancy than it is, but in practice, it's very important. It will allow us to go to well over hundreds of qubits without an added complexity in the classical control. The price we will pay, we don't have full connectivity anymore. It's going to be local 10 or 20.
Especially in the context of, say, VQE simulations and, say, especially for quantum chemistry, all the advantages of the ion-based platform that you described I think is very attractive, like all-to-all connectivity, very low gate noise, and so on. There's one thing which is a little bit concerning, and that's like, in the end of the day, if you want to train a VQE, you have to do many repetitions of the experiment, and if your objective function is a quantum chemistry Hamiltonian, you need to measure a lot of matrix elements. And then the clock speed at some point starts to become a problem. And the clock speeds are, well, as you said, in the 100 microseconds or maybe tens of microseconds range. So is there any hope to improve that?
So the question has to do with clock speeds, and indeed, the gate speeds are at best a megahertz. They're typically a significant fraction of a megahertz. And in VQE and QAOA, yes, there's a lot of signal averaging. You can't just take a one shot here. You know, the error bars I showed, we had to integrate. I don't know how long. It was probably a few hours or something. So yeah, it's a pretty serious thing. Now I would say on the one hand, there are ideas. In fact, I said right at the outset, if we do this force really fast, it actually gets simpler, so we don't have to worry about all these phonons. And to do things really fast, I mean, we have fast laser pulses, you just need more intensity. So there's a trade-off there, and with more intensity come other just practical issues. So we have a research project thinking about ultra-fast gates. They're not as high fidelity due to the stupid mundane things, so we're not using them in the laboratory for these algorithms. So you're right, the clock speed's an issue. On the other hand, I would say maybe what's more important is the time to solution. And if you have a fast clock speed, but you can only do a couple of gates, and as you make the system bigger, you can actually do less gates. Clock speed's irrelevant there, even though it's really fast. So yeah, this is something that we have to think about. You know, Alexei and others think about in sampling experiments how to coarse grain, how to get observables by sampling in ways that are smarter. But this is an issue. It's a challenge, I think, in all of these eigensolver, these variational techniques. You need a lot of data. Thanks for. I didn't answer your question, but I agree. It's an interesting point.
More questions?
So for the quantum machine learning type things that you're doing with the like bars and stripes, you mentioned you have like 11 or 14 parameters that you're optimizing classically. I'm just wondering, like, how does this compare to like a purely classical algorithm that like does generative modeling of that probability distribution?
Somehow this is not displaying. So how does it compare to a classical? Well, it's a 4-qubit system. And what's hard about that system is that what is the circuit that generates that particular state? It's almost a random state. It's a pure state. I guess classically, I don't know. I mean, I can't prove there's not a simple analytic circuit that you can just say you do these gates and you will make that state. I just don't know what it is. So the point there was not to compare the generation of the state with what you could do classically, because I don't know what that solution is. I think it more had to do with you know, straining the classical optimizer. It was more like 20, I think at the most we had 26 parameters we had to optimize in that system. And there we kind of couldn't do it classically.
I'm just wondering, like, order of magnitude, like, do you need a lot more parameters or like a lot fewer parameters for the quantum circuit compared to the classical, like?
But what are you comparing it to? Compared to the classical what?
Like just a classical generative model that models this probability distribution.
But it's not a probability distribution, pure state. It's a quantum superposition of these 6 out of 16 states spanning the Hilbert space.
Okay, but your goal is to get the probability distribution.
Well, the goal is to make this pure quantum state. Yeah, when you measure it, it's as though you had a probability distribution. I mean, if you want to make a probability distribution, just make each one of them with a probability of 1/6, just by dissipative means, I guess. So it's a little bit, I think I know where you're getting at. Maybe with 4 qubits, you're saying it's not very useful. I guess I would agree with that.
Next question?
Yeah, feel like making a stab at when you're going to achieve quantum supremacy? IQ, that is?
Quantum supremacy? Oh. Yeah. Well,
Not Wednesday?
Not Wednesday.
Not next Wednesday.
Well, it actually ties into the last question. There are lots of things that we're doing now that we don't know how to calculate. It doesn't mean that somebody doesn't know how to calculate it. And my understanding of quantum supremacy, it has to be backed up with a rigorous proof that nobody can ever do this problem classically.
No, I mean, same algorithm done on a supercomputer versus on the IonQ computer.
guess I'm not so interested in that. I'm interested in something that's useful. I mean, when you get to 20 or 25 qubits, our systems will be faster than a classical computer could simulate the gates. Because the Hilbert spaces, I mean, you can still do it classically, but the quantum computer will beat it. The simulation of the circuit. Of course, the circuit needs to be interesting to really claim something that you'd call an advantage. So I don't mean to be dismissive. I mean, we all know that there's a number between 40 and 80. When you hit that number, you pretty much can't simulate whatever's going on. And so, we're going to get there. Others will too.
Hi. So you mentioned one of the things you want to do is prepare ground states of typical condensed matter models or spin models and so on. Analog quantum simulators also try to do that, and then once they make the phase, they try to classify the phase by measuring response, like, for example, transport properties. Can you elaborate on some of the things you can do with digital quantum simulator?
Some of the things you can do with...
Like what kind of responses? You can't measure transport, I guess.
Well, the simplest thing is to, this will tie a lot of things together. The simplest thing, we started on this and other labs did as well many years ago, is to try to adiabatically find ground states. So prepare the ground state of a trivial part of the Hamiltonian, adiabatically turn that down. And that works with some success, but to be adiabatic with an interesting Hamiltonian, of course, the gaps shrink. And so in a sense, this is what QAO is trying to shortcut.
No, I understand.
So we're measuring ground states, but you're asking about non-equilibrium processes, and we're,
What's the point of making a wave function? You want to see what's the response of the system to understand the phase.
I think I get what you're saying. I mean, it's a dynamical question, and I guess I'm not going to I'm going to give you a fuzzy answer in that we're studying things like dynamical phase transitions that you might not expect because there's no equilibrium state here, but there's totally different behavior in the dynamics. It's not exactly transport, I guess. Well, yes. Our measurement is basically energy eigenstates, and you can certainly take snapshots if you twang the system. Like you can prepare, like in an XY model, you can prepare one up and all the others down and just watch that defect move through the chain. And with these long-range interactions, and Alexei and others have shown that you can go faster than these Lie-Robinson bounds moving across the chain. There's something called pre-thermalization that seems to happen, that things sort of get locked into place, and you have to wait for the tiniest gap to let itself be known. And that's behind what's happening in some of these demonstrations of time crystals. I mean, all these weird phases are kind of coming out of the woodwork due to the fact that we have all this control. Many-body localized phases that can underlie time crystals. So these are all a little bit scatterbrained ideas, but a lot of them come from condensed matter and indeed transport. So sorry, a little bit long-winded. Thanks for the help.
Last one.
Hey, Chris. I just wanted to add some comments on John's question and the second question. So it is indeed actually possible to solve for all normal mode problem in polynomial time, and you actually need the overhead that scales linearly in the number of qubits that you have in the system in order to actually do any XX gates in parallel, overlapping or not, while attaining the overall connectivity. It's just that if you actually go ahead and engineer the pulse in a more clever way, then you can take advantage of the locality that might emerge. That said, because you can actually solve for squarely many different XX gate controls, this could be one way to actually speed up the variation of quantum eigensolver, because if you have many of the XX gates that you have to apply in parallel, you can actually do them on without losing overall connectivity on ion trap.
Okay, so that's it. So we have now coffee break until 10:30. Let's thank Chris again.
This envelope in gray. And if we apply now dynamical decoupling to the MV centers, we are able to improve the coherence time. how much do we improve this coherence time? Well, it depends on how quick we can apply the dynamical decoupling, the spike pulses, on the NV centers. It tends to be quite faster than this coupling between the NV and the nuclear spin in order for it to be effective. If you were able to apply the pulses infinitely fast, so going down to a pulse spacing separation to 0, we would completely refocus this type of noise. Of course, this is practically not possible, but we are still able to reduce quite a bit the coherence time, or if you wanted, the decay rate of the nuclear spin, T2N, which is here renormalized with respect to the relaxation time of the NV center, the electronic spin, because this is what sets the total magnitude of our system. So if I didn't do anything, I would expect to be around here, 0.5. What is actually sort of counterintuitive is that for samples spacing separation, I can actually make my noise worse than it is if I didn't do anything. So this point here, which is above 0.5, and this is the theoretical line, show that if I apply my pulses at some wrong times, I could make things even worse. This is for our engineered noise. Okay? If we consider the whole system, it's the fluctuator is a 3-level system, while in the engineered noise we were only using 2 levels. And so things are slightly more complicated. We can still achieve perfect decoupling, but then we need to pulse between the +1 and -1 level of the NV centers. And this is a true photon transition, so you don't have that directly if you just use microwave driving. You have to do some composite pulses, or now we are also exploring some more crazy ideas of doing mechanical driving to drive that transition, which sounds quite interesting. So indeed, to reach here, you need this +1 to -1 driving. Otherwise, you would only reach this optimal point here. So here, what we can do, as I said, is limited at some point by how fast we can drive our system. And so what we wanted to ask was, can we then still take the knowledge that we have on our system and improve things even more by now applying real quantum error correction codes to this type of problem? And so here what we found was to look for some hardware efficient ways of correcting for one particular type of noise, this common fluctuator dephasing noise, which indeed appear in our system, but could be considered also more general, for example, some random fluctuator close to superconducting qubits, or other system in which you have, again, spins coupled to some nearby fluctuator. So it's a model, noise model that, of course, to me is very relevant because it appears in my system, but I think that it's more general. And especially the lesson that we learn by looking at this, I think it's indeed quite interesting. So what is the type of system that we have in mind? So again, we are thinking about mostly our NV centers, but it can be generalized to something broader than this. So in the NV center system, we have this electronic spin, and then we have, instead of considering just the nitrogen, we might also have some carbon-13 around the NV centers, which are also spin 1/2, and so they could be used as memory qubits, for example, in a quantum repeater scheme or for some other task. Again, because they still have some quite strong coupling to the NV center, on the order again between megahertz and kilohertz if they're close enough, the main source of noise is not the coupling to other nuclear spin, is not phonons, for example, but it's really the presence of the electronic spin nearby. And again, the idea is that you will have some energy which describe the coupling between the carbon-13 and the NV centers. And now how much energy the nuclear spin feels depends on the state of the NV center. Again, it will be plus this coupling G if the NV is in the +1 state, minus G if it's in the minus state, or 0 if it's in the 0 state. And this fluctuator will indeed jump between all these 3 states at random, so we cannot really know when the jump has occurred, and so we cannot really correct for that directly. But indeed, we know a lot about our system. So if I have more than 1 qubit, I know that if one error has occurred on 1 qubit because my NV has performed a jump, also all the other spin will have felt an error. and so the time at which this error occur are always correlated, which is quite different from a very generic type of noise model where many of these correlations are not really considered. So if I consider what is the evolution of each individual nuclear spin, it will acquire a phase, theta j, which is just dependent on what levels my NV center, my fluctuator have explored during the time of the evolution itself. Now I can also write everything in terms of a common theta by renormalizing my theta j by the coupling themselves. So all these angles, these errors are indeed random, but they are correlated with each other. And they have fixed ratio because they are just given by the coupling itself. I can expand my noise operator. So again, this is random, and so in general will give rise to dephasing. For small theta, I can expand in powers. And so to fourth order, at most what I will have is a sigma z error for on 1 qubit at a time. If instead I look at higher order, second order, third order, what I have is that I can also have a sort of a product between two different qubits, and so this corresponds to having error on 2 qubits, 3 qubits, and for the qt order, up to q qubits could have felt a correlated type of noise. So this is still a dephasing type of noise, so we could think about using the repetition code to correct for this. It's now a sort of rotated repetition code in the X basis, for example. So the 0 logical is the X plus 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 state, and the 1 logical is the minus minus minus, where these are eigenstate, the plus and minus of sigma x. And if I use something like this repetition code for larger and larger, I can also correct for higher order of my noise, but of course I will need more qubits. In particular, if I want to correct up to order q, I will need 2q plus 1 physical qubit, because the maximum error weight is indeed q. Instead, I can try to figure out if there is a code, a quantum error correction code, which is indeed optimized for this common fluctuator dephasing. And so we know that we only have an error on 1 qubit when there is also an error on all the other qubits. And so I can really exploit this knowledge. So I have this type of error and not each individual error on each qubit. Everything occurs all together. And so what I can do is to indeed try to impose, to correct just for the collective error, the square of the collective error, et cetera, et cetera. And so we can find some codes, and my student, David Layden, is credited with finding this particular code where you can then optimize this coefficient R in order to achieve indeed the code which will correct for the noise. And you can forward tune these phases alpha and beta in order to find something which is actually sort of convenient to implement on your particular system. With this type of code now, you only need a logarithmic number of physical qubits to correct for a given order in your noise. And this is, of course, we are still considering small devices. So it's not that we are claiming that indeed you will have an exponential advantage in terms of a large system, because this will be a type of noise which intrinsically will only apply to some sort of localized type of system. But still, even if you just look at a small number of qubits, you can see that there is indeed an advantage. So here what I'm plotting is as a function of the noise strength, so how probable one of these noise occur, the effective average error probability that will occur on your qubits. And so the black line is just when I don't do any error correction at all. And then I can force check for our repetition codes, for example, for 3 and 5 qubits, how much error I have if I do the encoding. And indeed you gain a little bit, but only for very small error rates. Now if I instead apply the particular error correction code that we have optimized for this type of noise, what we see is that I have quite a huge advantage. Indeed, is because for the same number of qubits, I can correct much higher order of my noise propagator. And so indeed, I can allow for a larger noise strength and still have quite a bit of correction. In order to find this code, we indeed need to know the couplings of the qubit to the noise, to the quantum fluctuator. And in practical terms, there will be always some like finite amount of precision with which I can know these couplings. And so we also check if indeed it was robust against some uncertainty in the coupling strength themselves. And so indeed, if you just have 1% uncertainty on the coupling, things do not change much. Okay, from here to here, you can see everything is sort of moved up a little bit. Okay, if we indeed increase quite a bit the uncertainty on the coupling, what you start seeing is that all the lines sort of collapse, and they, in the end, will tend to the repetition codes. But this is indeed what we expect. If we don't have knowledge of our noise model, then it doesn't make sense to try to find something which is tailored for it. So it's not really surprising, it's not really limitation. It just, again, reinforces the idea that if you do know your system, then you can do better. If you don't, well, you're stuck with just quite general error correction codes. Okay, we sort of try then to apply this type of ideas not to general quantum computation, but to a particular task, the task of quantum sensing. How much time?
7 minutes until the end of the talk.
Okay. So I think that this part is actually the longest one, but it's the easiest one, and so I will present it quite rapidly, I think. Again, it's just another example of how we can use knowledge of our system, but also how we can exploit the fact that we want to do just one particular task and not general quantum computation in order to achieve some good protection of our system. So what is quantum sensing? Well, quantum sensing, again, is for this particular talk, is just a parameter estimation. I have some external field which couples to my system through some parameter. Here, for example, the parameter is the field, and it's coupled to my spin through its geromagnetic-relation. In my mind, I always think about spins, I'm sorry. But this can be more general. It could be some electric field coupling to an atom, for example. What you do is to prepare your qubit in a superposition state, let it evolve for some time, it will acquire a phase which depends on the parameter, and then you map this phase into something that you can measure, for example, population difference, and you measure it out. The signal-to-noise ratio, of course, is proportional, because it appears in this phase, to the coupling strength between your field and your qubit, and to the time that you let your system evolve. Of course, both of them are sort of a trade-off. If your system is very strongly coupled, then this gamma is very large, but your coherence time, the time that you might be able to let the system evolve freely, is limited by the coherence time. And so what you can have is something very strongly coupled, very big gamma, but your coherence time becomes very small. So this becomes very quickly just a classical sensor, because coherence is lost very quickly. In the opposite regime, we have something which is very long, very long-lived, very long coherence time, but most probably it is because the coupling to the external world is very small. And so what you have is a quantum memory, not so much a sensor. And so our question is, can we use error correction to do better, to find a better trade-off between these two limits? Can it help us? And the idea of quantum error correction for sensing is very similar to what is applied in computation. Instead of having just a long time period during which you will acquire a phase, n time the phase that you will acquire in the unit time period, you interrupt it and apply some recovery operation in between to check if noise has occurred and correct for particular errors which might have occurred. What others have found are some conditions under which error correction for quantum sensing can indeed be applied. And the idea is that you still need all the conditions for quantum error correction to work, of course, because you're doing error correction, but there is still this trade-off which is intrinsic to quantum sensing. Whatever you are trying to sense is an unknown quantity. It's a coherent error, typically, so it's a coherent interaction, but it's still something that you do not know. And so it looks very similar to some type of error. And so if you apply just a generic quantum error correction code, most probably it will also cancel out whatever you want to measure, and that's not really good. And so there is still this trade-off between try to protect your system as much as possible, in this case through quantum error correction, but try still to save the coupling to the field that you want to measure. What people found was that indeed, in a very intuitive way, if your noise looks too similar to the signal, then it's not possible to find the code. Only if the noise is somehow perpendicular, it doesn't really exist in the same plane as your noise, then you can distinguish the two. And indeed, how many people interpreted this was that if you had dephasing noise, maybe you could measure something along the sigma x direction, but you could not measure something along the z direction. But looks like a very intuitive interpretation of what these rules sort of give you. Other drawbacks of this particular proposal for error correction for quantum sensing was that it was required to have noiseless ancilla. And as we said, there are some good low noise ancilla, but typically they're not completely noiseless. So we wanted to find something a bit more practical than this. So what we then investigated was the fact that maybe there is something else which can distinguish your noise. So as I said, the picture from which was taken from here was to say, okay, I have noise along Z, let's measure something along X. But there might be something else which might distinguish your noise from your signal. When we do dynamical decoupling, that something else is frequency. Okay, so your noise spectrum sits at a different frequency in the signal that you want to measure, and so you can distinguish it. You can use, if you want, algebraic differences, x and y direction, x and z direction, but you can also try to use spatial correlation in order to distinguish between noise and the signal. And so, again, we looked at specific examples of particular noise model in order to figure out if indeed it was possible to practically find some error correction codes to do quantum sensing. And so what we wanted to do was, again, to measure something which is just an energy shift, okay, which is typically what any sensor is most sensitive to, in the presence of some noise which is still a type of dephasing noise. But now this dephasing noise has some correlation between the noise which happens at different qubits encoded in this matrix of correlation here. Still, even if they are all along the same direction, you can find some error correction code provided that this vector describing your field is not all in the correlation matrix here. So we could find some example with 2 and 3 qubits where things are easy to calculate. For 2 qubit, actually, this boils down to just the coherence-free subspace. Or maybe you can measure differences in the field and have a sort of a uniform type of noise. For 3 qubit, you can have, if you want to measure uniform Z, one possible code is the repetition code, depending on the various correlation that you have. But you can also have some more general and different type of codes if indeed your correlation matrix has some particular shapes. So for example, for this type of shape of your correlation matrix, we could find that if I don't do anything, I lose my coherence quite quickly, and so my sensitivity is not as good. But if I apply my active error correction codes, I get much better sensitivity. So the lower the sensitivity, the better, because you can sense smaller qubits. We extended this to more general condition under which you can indeed achieve quantum error correction for quantum sensing when you don't have noiseless ancilla. And the condition is that you need to have that all your Lindblad are commuting, and they're also commuting with your Hamiltonian. Under this condition, you can indeed find error correction schemes which do work even if you have ancilla which are all affected by the noise itself. And in collaboration with Yang Zhang at Yale, we found some example from this dephasing noise that typical in NB centers schemes, but also for bosonics channels. More generally, you can think that, especially for quantum sensing, the goal is not really fault tolerance. As long as you apply some error correction code, which just improves your sensitivity, even if you're not noiseless, then you're still winning. And so you can potentially find more general codes there, and indeed you could sort of apply approximate error correction codes based on what we found, but it would work out quite well. So before concluding, I actually want to give all the credits of this work to my students. Mo worked on the quantum fluctuator project, and David is the mastermind of all our theory work on quantum error correction, so all the credit to him. And now we are working together to actually implement this idea of the hardware efficient quantum error correction codes in our NV Center system. So I'll leave you here with my conclusion and take any question that you might have.
Thank you, Paula. Questions?
Thank you for the talk. Hi, okay, thanks. I think you used this error correcting codes for spin defects, but is it possible to do it for like resonators or like cavity QED or circuit QED setups? So
as long as you have some sort of fluctuator which affects different qubits in a correlated way, then yes, definitely. And I think that like some of these like random fluctuators, they do appear because they're sort of correlated to materials impurities. And so I mean, of course we use it for our system, but I think it's more general than that. And of course, like this random fluctuator model is one particular model that we study because we did want to do the experiments in our system. But there are other models for which we hope that you might be able to find like Taylor error correction codes, which again will save you some hardware.
More questions? Maybe we can ask one quick question. So is it I guess in this situation where you have this common fluctuator, I guess unless all the G's are equal, there's no decoherence-free subspace?
Yeah.
Too bad.
So
because it seems there's only one error and like so much Hilbert space.
Yeah. So, but in some sense, the code which like you end up creating, especially for small number of qubits, is relatively simple. So you don't need all that much of entanglement. So a lot of it is actually just separable state, which is quite different from a usual error correction codes. And I think that it's indeed related to the fact that it's quite close to a DFS in some sense.
More questions for Paula? Optimally positioned to be just way distance from the two of us.
I have a question about the common fluctuator and when you have uncertainties in your couplings, the plot that you showed. Have you looked at optimizing the code for multiple G's within the uncertainty that you have at the same time? Like taking the mean of the cost function that you're optimizing for multiple values of G?
No, so here basically we optimize assuming that we know a particular set of coupling, and where we say, oh, well, we were wrong, and so how bad it would have been. But I mean, it could be interesting to potentially indeed do the optimization over a range of possible coupling, which I guess it's what you
exactly.
Yeah, so yeah, I agree, but we didn't do it.
Thanks.
Yes.
More questions for Paula?
We should do it for the experiment where we probably do have uncertainty, and the number of qubits is going to be 2, so that's quite feasible, yeah.
More questions? If not, let's thank Paula again.
show you these things will be until the end of the talk. So you'll still have like 10 extra minutes when it's done.
Let me see.
So our next speaker is Lorenza Viola, and she'll talk about noise characterization for NISQ processors and beyond.
So let me start saying, do you hear me fine, the microphone? If it does weird things, just wave and I try to not to move around. Alexi, thank you so very much for having me here. It's a wonderful opportunity and a great place too. I will start with actually a quote. The title of this slide is not coming from me. I was listening to a talk by Jim Weaver at IBM, and I really like the reminder that N in NISQ is for noise, and noise here will be used in a pretty generic way. It can encompass background noise, decoherence due to all kinds of bad things that can happen, but also control noise. And this will be important, as we heard from Chris. For instance, atomic systems do not suffer that much about environmental noise, but it's all about the control. Not so for other cases. I lost my mind. Okay. So anyway, I would like to take the philosophy that if we really want to push the capabilities of NISQ processors as far as they can go and deliver all the good quantum advantages we can hope that they will, then this will demand for sure a continued and, in my view, pretty sustained effort in reducing noise levels, and also, on top of it, optimizing the circuits themselves. So, in order to achieve this noise reduction, I will argue that it's certainly a good thing to get to learn as much as possible in a quantitative way and in a predictive way the properties of the noise we're actually fighting for in an actual platform. So in talking about noise, I would also like to say that noise is ubiquitous in the classical world and not just in physics. There is a whole branch which is statistical signal processing, which is pretty much devoted to developing techniques, both analytical, numerical algorithms, for studying signals which are actually the noise itself. And this is the entry you see in Wikipedia, in particular for one of the things we always do when we think to noise processes is like trying to resolve them in some sort of components along a functional basis of interest. Let me just, for concreteness, imagine here that we have stationary noise processes which are time translational invariant in their statistical property. So the relevant picture, the relevant basis is Fourier basis. And so in that case, the goal of all of the techniques in signal processing estimation is to come up with ways to estimate the relevant set of spectra which characterize the content of noise in the frequency domain. So in our case, of course, we are quantum, and so spectral estimation in the quantum domain is quantum spectral estimation. Also, we call it, it's a name that has become very popular, quantum noise spectroscopy, and what we aim to is to achieve spectral estimation in the target open quantum system that is representing our NISQ machine. I think Paul already made quite a convincing case as to why having detailed noise knowledge is useful, but let me also add on my own. I think that there are various reasons for that, and to me, I have been long interested in decoherence modeling in itself, and truth is, this is not true. I don't know if Chris is still here. I agree that is not the case in atomic system, but certainly in solid state, more complicated type of devices. We don't actually know very well, or certainly in full, the microscopic nature of many of the relevant noises and the noise mechanisms. And I thought that a good case in point, this is a preprint that was posted only a few days ago, and it points out from McDermott Group of a study that is done on a variety of superconducting qubit, although here the device was operated more as an SET. The bottom line is that the type of charge noise that they see in this device does not comply with what the typical fluctuator-based model would predict. So there is in particular an unexpected dependence on the device scale, which means that we better try to get a more accurate picture, because this can impact, even though maybe at the current scale this knowledge will be okay, a complete picture will be necessary as we are trying to scale up further. And that's the main fundamental reason to me. The second one, as we heard, and that to me is actually a very wide lesson from dynamical systems, from theory, from control theory, because whenever we can gather knowledge about the plant, the target system in question, then we can devise all kind of control techniques, of which error correction is one of them, dynamical decoupling is another one, in a way that we can call to be noise tailored, or even better, noise optimized, maybe at the cost of losing some model robustness. We have to be careful in that, but certainly there are going to be, as Paula clearly made a case for, there is a lot of practical gains to have. Indeed, I also wanted to note that we already know that even pretty simple, pretty basic quantum control techniques like DD implemented in the most rudimentary NMR, like this is an XY4 implementation that was done in this paper by Dan Leader group on actually two current, the IBM and Rigetti machine. Well, what they have seen as a function of the initialization of the, I think is like 5, and then I don't remember how many qubits, but that's not the main point here. The main point is that even using very simple, basic sequences does give an improvement in terms of reducing, for instance, the storage, the sensitivity of the storage time to the initial state. So the bottom line here is that if we really get serious at understanding the actual noise, and we try to optimize, in this case decoupling, but it could go for dynamically corrected gate, it could go for composite pulses, and so on and so forth, probably we could get a lot of further improvement in these machines already. Lastly, I would also note, although I will not expand at all on this, that there is a whole another chapter in some sense on which noise characterization has to come in and become important, and that is the level in which at some point it will have to be integrated as we are thinking to larger and larger scale quantum circuits to be executed. There has to be a way to incorporate actively the characterization of the noise into the algorithmic, into the compilation of the circuit, so that we have both at the physical and algorithmic level some degree of built-in noise resilience. Lastly, in terms of my motivation, I like to stress that there is more to be gained about having good understanding of noise, even beyond NISQ, and even beyond quantum computation per se. So I would like to me, it was very enlightening when finally realizing how much, and John is here, how much the properties of the correlation, the noise correlation, temporal and in particular spatial, have to do with the very possibility that we can achieve fault tolerance. And validation of this, the spatial behavior of this noise correlation will be, in a given machine, actually determining whether or not we can go the full way to the fault tolerant scale. Also, we already heard from Paola, her last talk was, example was all devoted to the importance of noise characterization for sensing and possibly error correction. So this is what she already mentioned. I'd also like to mention the work on my own, on my group, where we actually see that if we have some sort of spatio-temporally correlated environment, well, it becomes really important to be able to know it in detail, because otherwise, even if we use entanglement assisted metrology with squeezing, that can negatively interfere with the squeezing that the bath is able to induce and basically nullify every possible advantage. So with that, I hope I have conveyed the importance of the topic, at least to me. So the idea or the basic philosophy here is, well, qubits can be very, very sensitive spectrometers of their own noise, so why don't we try to use them? And a quantum noise spectroscopy protocol at a high level looks like something where we have a qubit-based sensing system. In the simplest possible case, one qubit sensor that will have to be able to control with some capabilities, and we'll have to be able to, of course, measure. With the measurement of suitable observable will encode the information of the noise that is acting on this system as it evolves, and then the task of the proper spectral estimation task is how to deconvolve out of the observed, for instance, expectation values, how to deconvolve these complicated typical overlap integrals that come up in the reduced dynamics to get the information we want to have. So from a point of view of spectral estimation, there are various flavors of the problem. In particular, we can have parametric or non-parametric types of estimation protocol. A parametric one makes some assumption about functional behavior of noise that we might have with some unknown parameters, so it's kind of a parameter estimation. The type of instead protocols that I will be mostly focusing on are so-called non-parametric, and they really aim to output estimates of the power spectral density, or as you will see, set of power spectral density and spectra that are of interest. I have said that we need to be able to control the sensor or the sensors in question. This can happen through either multi-pulse protocols, or it can happen by means of continuous wave drives, and all of these will have to be designed in such a way that combined with the capabilities for measuring the systems we have at hand, we can successfully do the inverse problem and the deconvolution problem that gives us the estimation. So these sets of ideas, they have been, there are various approaches that I am really alluding to here, and more are being proposed as I speak. They are kind of pursued, assessed in parallel with one another, both on the theoretical and the experimental side. I have no time whatsoever to review a lot of experimental validation that have happened throughout a variety of both atomic and solid state superconducting, semiconducting, and NV platform. But let me just stress that all of these experiments I have summarized or alluded to here, they are happening at the single qubit level. They use a single qubit sensor, and they mostly try to characterize noise, assuming that the system is phasing dominated. Looking from a materialist, so of course I like to look at the challenges, the theory challenges that come with these issues, and there are several that we still have to work towards before being able to have a sufficiently general toolbox that I like to say could be applied to sufficiently complex systems such as intermediate scale noise environments that are of relevance to NISQ. So I would like to say that there are very important practical limitations that stem from spectral leakage, which is a very old problem also in signal processing, but I will not talk about this. There is work that I've been doing in collaboration with BIRSEC group, which uses a particular time of optimally band-limited limitation, Slapians, but for the sake of time, I will focus on two other aspects, which is related to two main points. First of all, in a lot of the protocols that have been designed and used so far, there have been pre-existing assumptions that have been made, such as it is a priori assumed that the noise statistics is Gaussian and we are in a valid semi-classical regime. Whereas if we take the point of view of aiming to kind of a black box characterization one day, I don't want to disprove that in many cases of interest, certainly a classical description will be okay, so will be Gaussian statistics, but we would like to see these as a product of the validation procedure rather than being built in as assumption to begin with. So how to cope with that, and also what distinctive features to look when we have classical or non-classical spectra. Secondly, like I mentioned, a lot of emphasis has gone into single qubit characterizations, but it's all about the correlations. These are going to become more and more prominent as we look ahead. And so how can we use multiple sensors to detect, beginning from 2-qubit spatial correlations, and then can we do so maybe in a dynamic way, so down the line, can I also relax, which is not something that I will touch upon in the talk, this assumption of stationarity, which is one that I will maintain for the rest. So in the rest of the talk, I would like to basically describe some of the steps we have taken to tackle some of these questions. I wish I could answer them all. I don't have an answer as of now. But some steps that for now will focus in this talk on single axis noise. I mean, dephasing will be the dominant noise to be considered in these theoretical protocols, as well as there are experimental validations that I will allude to that are done with superconducting qubit system in collaboration with the group of Will Oliver at MIT. And with that, I will mention how to carry the idea of high-order spectral estimation, which is spectral estimation beyond just the two-point correlation function, beyond the Gaussian regime, to the quantum domain. Doing an estimation of not only the spectrum, but the first high-order leading bispectrum of the system. And then I will also, probably this is where I will run out of time, but mention the possibility to actually do a full 2-qubit quantum noise spectroscopy protocol to detect and to characterize the spectral properties of correlated spatial noise. And this will involve two different techniques, so let me get without further ado to give you the basic, the gist of both of them. Like I said, the experimental partners at MIT, the main graduate student for the first experiment, which is available in the archive, is under review. And then on the theory side, my former postdoc, current postdoc, they definitely helped a ton to make this possible. So, background here, like I said, we have 1-qubit sensor. It couples to a dephasing environment. And that means I will assume the quantization axis in Z as usual. And what I am going to be particularly interested in is the coherence property as it changes as a function of time of the qubit as with respect to the initial time. And notice that I am parameterizing this in terms of two
I cannot say parameters because they are functions of time, but there is a decay function that is taken to be real, and also there is another phase function, so this chi and phi are both real, and in general, they are both going to be present in determining the time evolved off-diagonal matrix element of the qubit. So the noise properties are going to be as usual, except that my operator could be a quantum operator, so I have to be careful about ordering time, but we have connected correlation functions. And if we assume stationarity, which means that all the properties depend only on the mutual time separation, we can go to the Fourier domain and look at the Fourier transforms of the correlation function, which is what gives rise to, usually when we have only the two-point correlation function, which is time translational invariant, we have one variable, so we have one Fourier transform, which is the power spectral density or the spectrum. However, in general, when we have non-Gaussian statistics, such as, for instance, Paula mentioned random telegraph noise, that's a classically paradigmatic non-Gaussian stochastic process. Well, in that case, in the Fourier domain, we have, in principle, a whole infinite family of polyspectra, which corresponds to the Fourier transform of the high-order correlation. All right. So in the simplest case where the sensor here is going to be controlled by sequences of nearly instantaneous pi pulses, it's very easy to describe the effective dynamics in terms of certain switching function that determine the plus or minus sign in front of the sigma z operator where the switch happens at the time at which we apply the pi pulse. And in the Fourier domain, the control is encapsulated by the corresponding finite time Fourier transform. The nice property, or one nice property that we can recognize is that if we work in frequency space, all the possible filter functions that I can come up, they can be packaged. I'm not saying in a simple way, but they can, in terms of just this one fundamental filter function that we have here. So we can express the decay, we can express the phase in terms of cumulants, and something which is very pleasant is a simplifying feature of the problem is that actually only a cumulant of even order, so if you look at the sum that we have here, only even order corresponds to the decay, which is why when you have the familiar case of Gaussian noise, you just have that one that contributes here, and instead only odd order, like the mean and the third order, corresponds to non-Gaussian, corresponds to the phase evolution, which gives us a distinctive phase signature, which will not be present if the noise is Gaussian. That is what I'm going to be using for my non-Gaussian signature. So how to abstract, how to go and get a spectral estimation of both the spectrum and the leading non-Gaussian contribution. This is involving ideas which go back to Alvarez-Suter on repeating a sequence, a decoupling sequence in time, so that essentially we can have the filter function combining in such a way that they give us a frequency comb, and the frequency comb in the noise in the Gaussian approximation is able to be used essentially as a grid for estimation at multiples of the harmonic frequencies. So if we would do that in the Gaussian noise approximation, we measure a bunch of decay parameters through different experiments, and we have each of them is related to a sampling of the spectrum at multiples of the harmonic frequencies. So the problem boils down to to solving this linear system of equation and getting an estimate of the spectrum. For the non-Gaussian case, however, that's not the only thing we have, because we would also like to be able to estimate the leading order spectrum, which has in the case at hand, the one I will be interested in is going to be a bispectrum. And for classical processes, we can leverage symmetry properties that high-order spectra have. Bottom line is that we can still set up an inverse problem through which, this time, measuring not the decay, but measuring that phase evolution that the qubit picks up due to the odd-order cumulants, if we are able to solve a suitable linear system of equations, we can get the desired estimate. This was the basic idea that was implemented, in this case, in a single qubit superconducting, a variant of the flux qubit, which, however, has more anharmonicity built in. For the experimental is in the runes, I can expand later, but the key feature that was used to validate this protocol is the fact that if the qubit is operated near the sweet spot or the degeneracy point, the qubit transition frequency has an approximately quadratic rather than linear dependence upon the applied flux that biases the system. So pictorially here, if we are parking the qubit in a place where the response is linear, then any input noise through the flux degree of freedom will remain Gaussian if it is initially Gaussian, and that is what we in this cartoon illustrate. However, if we park the device at a point where the response is nonlinear, and here it is quadratic, even though the flux noise could be taken to be Gaussian, and in this case we actually engineered it to be Gaussian, the fact that there is nonlinearity in the system automatically transduces it to non-Gaussian frequency noise in the qubit. So we are back in business. We have non-Gaussian noise. Here I can connect to the theoretical quantities I was talking about. I have a non-zero mean for the resulting noise process. I have a spectrum, and I also have, here it is, the leading order bispectrum that comes from the Fourier transform of the three-point correlation function. So I will, of course, not go through the detail of what was a very complicated experiment because the non-Gaussian signature is weak to measure, but suffices it to say, the upshot is that we were able to, yes, reconstruct, obtain an estimate of the spectrum, the power spectral density, by using a suitable set of control sequences, actually 11 of them that would be repeated, not that many times. So it was there were a lot of non-idealities involved in the implementation that we didn't have in the theory, so we had to work on. But in the end of the day, we were able to extract the information that we could use to reconstruct also the bispectrum of the system. This, to my knowledge, is the first time that like a bispectral estimation was attempted on engineered noise, but in the quantum domain. There are error bars, and these should be repeated and done better, but it's a first step there. So I know that I am almost around. I will just take a few more minutes to sketch the second, and this is actually still unpublished. We are still polishing up the data analysis, which is significantly more complicated here. Same to senior people, but in this case, the lead graduate student was Uwe von Lübke, and the same theory guys helping out here. In this case, we took qubit in a still dephasing dominated setting, and assuming that I will just want to do Gaussian spectral estimation because this is complicated enough for starters into qubit. Now the indices are labeling different spectra for qubit, because when you have these indices equal, like S11 and S22, we call them self-spectra. They characterize a single qubit noise. But the important thing is that now there is a cross spectrum that can characterize non-trivial correlation, noise correlations that exist in the system. So in this case, protocol using the dynamical decoupling pulses that would be able to do it. For reasons related to the implementation, we decided to go with a different type of control modality, which is rather continuous wave. It is inspired for the NMR people in the room to T1 row relaxometry. Basically, the idea is that if we have our qubits, which are predominantly exposed to the phasing noise in the lab system, if we drive them coherently, we can bring them, we can make a transformation to a tilted frame, to a rotating frame where the quantization axis is tilted, and essentially, if we work out, we started from the phasing noise, but if we look at it in this tilted basis, it becomes like an energy source which can induce emission and absorption, and it does so. This is a master equation that we were able to derive under various assumptions, but it induces correlated emission and correlated absorption at a frequency which is tunable, because that turns out to be the amplitude of the applied drive. So with this, in this case, one way in which we can think about the estimation problem is like we have the capability of initializing the 2 qubits in a variety of initial states. We only choose product states in the spin-locked basis. We give ourselves the possibility to simultaneously do projective measurements and infer the values of a set of observables, which are listed here. There are several times. So bottom line, we're going to have data from the experimentalists that come to us in a big set of sample means, which I have collected up here. And all of this, we could, because I came up with a model master equation, we could try to compute theoretically, to do an expected value theoretically by solving the master equation, which contains all of the spectra that I want. So at that point, the problem can be viewed as a nonlinear regression, where we can try to essentially determine the spectra, all of the spectra in question, by trying to see which choice of the parameters in the models is globally minimizing the deviation of the estimated or the computed observable via the master equation with respect to the actual data. And this lambda here this has to do with the way in which we actually implemented the estimation. We didn't just do a plain weighted square fitting because we had outliers, so we had to do something statistically more sophisticated, picking a different loss function. But the bottom line is that out of this pretty massive problem numerically to do, we can get out estimates of all of the spectra. Doing so, actually, this is a picture, the parameter of the actual system. This is a circuit QED system. In this case, we have the 2 qubit, but they are also coupled to a shared microwave resonator. And the resonator is able to be, let's say, controlled to the point that for validation purposes, it was put in a state where the number of photons in the resonator was known with good accuracy. Bottom line is that by working with this system and removing the resonator mode from the picture, we are actually working with spectra, which are typical Lorentzian spectra with photon shock noise type of statistic behavior. And these are the ones we want to reconstruct. And that's pretty much the last thing I will show. These are the reconstruction of the self spectra. They are real. And notice that they are not symmetric about the zero frequency. That's the signature of their non-classical nature. Is photon shock noise, so it doesn't, it's not obeying the symmetry property that classical stochastic noise processes have with respect to frequency. And the plots in this second row, instead, they clearly show not a significant correlation, spatial correlations, which exist in this 2-qubit system via the real part and the imaginary part of this cross-correlation spectra. And I could tell you after how we actually did the simulation, which is via full system numerical simulation. I will put up my concluding slide. Still at the single qubit noise characterization, what we are doing and finishing up right now is also protocols for, I have said that I am estimating dephasing noise. We can actually do better than that and estimate simultaneously like T2 and T1 together, so multi-axis noise. And we can also simultaneously estimate background and control noise. So these are two papers that hopefully will be done soon. The challenges that remains, let me just iterate something that I already mentioned, is how to integrate all of these small capabilities into a toolbox that truly is usable and useful for NISQ machines right now. And with that, I apologize for the extra time. I knew it was happening, and I would like to take questions.
Thank you, Lorenza, for being actually very much on time, on the contrary. So questions for Lorenza?
Hi, thanks for the great talk. I had a question about the 2-qubit stuff and actually kind of extending this beyond single and 2 qubits. Clearly there was some very clever thought on the team involved in figuring out the dynamical equations that correctly model the system in order to be able to do the noise spectroscopy. So do you think this is a scalable approach moving beyond 2 qubits?
No, I actually don't think we can go with this type. I would still view this, thank you for asking, it gives me the opportunity to expand on what I had in the concluding slide. This is still kind of brute force. And I think it is doable and should be done at the level of single and 2 qubits within NISQ machines. In order to try, for instance, it's not obvious to me that all the 2-point correlations will be the same, so there might be different behavior there. But one of the bigger challenges is like how to actually think about a characterization of a 10-qubit, a 20-qubit device in one shot, in some sense. And for that, I don't have a final answer. That's something that definitely I will think more about. But there could be ways for integrating with robotic techniques, with more automated techniques. And also, there has to be some sort of, we need to understand a trade-off between, yes, noise characterization, I've made a big case in favor for it, but how much really, we can't aim for full detail as the system scales up. At the same time, we don't want to lose too much detail, and I am not clear on where a good metric for assessing how detailed is detail enough for the task that we want.
More questions for Lorenza?
I wasn't quite sure, so maybe you can comment. Is what you found experimentally for the 2-qubit correlated noise good news or bad news or in between news?
In this case, I wish I could have an answer. I don't, because we actually only validated the protocol on a type of 2-qubit correlated noise that we engineered with known properties. So, of course, the next step, once we know that the protocol works, would be to try that's really something that should be run, maybe in some of these very superconducting qubit platforms such as IBM or Rigetti, to see what their noise correlations are. Because there is evidence, I didn't say, but there is evidence that, for instance, some of the IBM quantum experiences and the Acorn and Rigetti, they do have spatial correlations. The point is like how harmful are they, and how do they behave as a function of the geometry of the system.
So following up on the topic of testing this on NISQ devices, in particular these publicly available NISQ platforms, what sort of changes, if any, to the existing interfaces and control that end users have to, say, IBM or Rigetti devices need to be put in place in order for somebody to just be able to do these same sorts of experiments?
This is not entirely clear to me because I'm not fully familiar. I'm trying to look into it, but for instance, in the IBM, for sure, in the versions that are or were publicly open source, there are only certain type of pulses, certain types of angles. And for the 2-qubit, this protocol in particular instead was using continuous drive. So I honestly don't know. I didn't have the time to look at these things, but certainly people at IBM are interested in looking into, now that they have open pulse capabilities and things like that, and they are very much inspired to NMR, these protocols, both of them. So I would hope that they are not too taxing in terms of their implementation.
More questions for Lorenza? Okay, so if not, so just we will clap in 1 second, but don't leave after you clap because I want to say a few more words about lunch. So let's thank Lorenza and the rest of the speakers in this morning session. So we'll have 2 hours for lunch, and make sure you come back on time at 2 because John will be speaking, and Goran will now tell us about the lunch option. Unfortunately, unlike at TQC, there's no provided lunch, so that's why we need to say a little more about it.
But there are 2 hours, so plenty of time to explore. So if you go to the website and you go to travel and venue, there's a map here where everything's marked. So here's that map. So we're right here. So this is the Ariep Center. This is the hotel at UMD where TQC was. So there's basically sort of 3 main options. One is to go kind of further into campus, sort of that way, and to go to the Student Union, which has sort of a bunch of kind of mall food options. The other 2 options are to basically go up Baltimore or down Baltimore. So, there's the restaurant inside the hotel. There's a nice restaurant in the Cambria Hotel. There's several options here and quite a few options down here. So this is about half a mile away, so that's plenty of time for that. But be sure to be back at 2 p.m. for John Preston's talk. Thanks.
It's like basically the same setup as in like the standard model. announcement about the. Okay, so welcome to the afternoon session of the first day of this NISQ workshop. I just want to make a brief announcement before we get started with the talk, which is that there will be a photo done for the workshop, which is going to be at the end of this session. It's going to be held outside, so in the grass, kind of facing the building. So we'll make another announcement as well at the end. But we'll go out the doors, and there will be folks directing you to the outside where we'll take that photo. Without any further ado, it's a pleasure to introduce John Preskill from Caltech. John has given us not only the term NISQ, but I think also a lot of insight into what we might try to do in the NISQ era. And today he's going to tell us about quantum speedups in the NISQ era.
All right, thank you, Andrew. I made up a word. They named a workshop after it. And people came. It's pretty cool. Graham Smith asked, why aren't we calling this meeting NISQ Business? It seems like a missed opportunity, but I'm thinking that if I decide to get a new puppy, I'm going to name her NISQ. As we've heard, NISQ means noisy intermediate scale quantum. Devices of sufficient scale that we can't simulate them by brute force, even using the most powerful available classical supercomputers. But noisy reminds us that these devices will not be error corrected, and noise will limit their computational power. So for physicists, NISQ is quite exciting. It means that we have the opportunity to explore the properties of complex, highly entangled states of many qubits in a regime which has not been experimentally accessible before. And there may be other applications besides that, but we're not sure about that. We shouldn't think that NISQ is going to change the world by itself. Rather, it should be regarded as a step towards the more powerful quantum technologies we expect to develop in the future. I'm actually optimistic that quantum technology will ultimately have a big impact on the world, but we're not sure how long it's going to take. Why is NISQ exciting? Well, to put it succinctly, in what could be the watchword of our discipline, classical systems cannot simulate quantum systems efficiently. And you could argue that that's the deepest thing that we've ever said about the difference between quantum and classical. So everyone in the room believes this, right? But we can't actually prove it. What are our reasons for believing it? Here are some of the reasons. We know of problems that we believe are hard classically, for which we have efficient quantum algorithms. Factoring is the best known example, and we think factoring is hard because really smart people have tried for decades to come up with better factoring algorithms, but the best algorithms we have still have a runtime which is super polynomial in the size of the number to be factored. We have arguments from the complexity theorists which say, for example, that I can run a relatively small quantum computation and measure all the qubits, and under plausible assumptions, we can argue that in doing so, we are sampling from a probability distribution that we can't sample from efficiently by any classical means. But maybe the best reason we have to think quantum computing is powerful is that we just don't know how to simulate a quantum computer with a classical one. And it's not because we haven't been trying. Physicists and chemists have been trying for decades to come up with better methods for simulating highly entangled systems of many particles, but the best algorithms we have still have an exponential runtime in hard instances in the size of the system. We don't think, though, that quantum computers have unlimited power. We don't expect, for example, that we'd be able to find exact solutions to the worst-case instances of NP-hard problems efficiently with a quantum computer. So this is what our map of the world looks like. And we're trying to fill in some of the details. But we still don't know a whole lot about that terrain, which is classically hard and quantumly easy. And from some perspectives, that's not so surprising. Since we don't think quantum computers can efficiently solve the NP-hard problems, at least within NP, we're talking about problems that are not NP, but are not NP-complete. And those have a rather special structure. In fact, some of them are suitable for constructing trapdoor one-way functions. From that point of view, it's not surprising that quantum computing has something to say about cryptology. But for a physicist like me,
even if it couldn't do anything else, there would be a very strong incentive to realize large-scale quantum computing for the purpose of simulating complex physical systems. I've spent a lot of my career thinking about things like what happens in strongly coupled quantum field theory and what happens inside a black hole or in the very early universe. Arguably, these are phenomena which are hard to simulate on classical computers, and to do it with a quantum computer eventually will, I think, be very empowering and exciting. I've emphasized the number of qubits as a milestone for quantum technology. Of course, it's not the only thing we care about, as we heard this morning. We also care about the quality of the qubits and especially the fidelity of the 2-qubit entangling gates that we put together in a quantum circuit. And the situation now is that under the best conditions, with superconducting or trapped ion processors, we can do a 2-qubit gate with a probability of error per gate of about 10 to the minus 3. We still haven't seen whether that's possible in larger devices, complex devices containing many qubits. So naively, we can't expect to be able to execute circuits with more than a few thousand gates and read out the answer with useful signal-to-noise ratio. Even in that case, we'd probably have to run many times an average in order to estimate with some statistical significance the expectation values of observables we care about. Eventually, we know there's a way to do better using quantum error correction, but because, or perhaps by making much, much more accurate quantum gates, but in the case of quantum error correction, because of the high overhead costs and additional qubits and gates, that's not something that's likely to happen very soon. So what do we want? We want quantum speedups. We would like to be able to solve, ideally, some interesting problem with a quantum computer which surpasses what we can do with the best classical devices. To make a fair comparison, we should consider a classical computer which is running the best algorithm on the best hardware for solving the same problem. And maybe we should look out a little bit at what that classical hardware might achieve a few years from now when quantum computing might start to become competitive. And we should also have in mind the vexing problem that it might not be so easy to validate, in the case of problems beyond NP, whether the quantum computer is really getting the right answer. Now, we already have seen a number of times the lesson that sometimes we can make overly optimistic projections about what's needed to demonstrate a quantum advantage for some problem. And I won't go through this list. It could have been a longer list. One that I find particularly poignant is just a year or two ago, I'd like to point to the Karanides-Prakash algorithm for quantum recommendation systems as an encouraging example of an application of quantum technology that, at least maybe not in the NISQ era, but eventually would be valuable. But Ewing Tang killed that off. There may be an interesting polynomial speedup, but it's less exciting without the exponential speedup. And the other thing that kind of catches your attention from time to time is how the classical methods for studying quantum problems, tensor network methods in particular, have continued to improve. And they can compute a lot of things now that they couldn't say computers and which quantum computers can solve. Well, if that depresses you a little bit, this is supposed to buck you up a little. I learned this from Nevin. I'm calling it Nevin's Law in his honor. He says that the classical resources that you need to simulate a quantum computer are actually growing doubly exponential in time. The argument is based on some rather dubious assumptions, but I'll tell you the idea anyway. You might argue that, looking at recent history, that 2-qubit gate fidelities have been improving exponentially in time. And that means, roughly speaking, that the volume of a quantum circuit that we can execute reliably with a quantum computer is growing exponentially in time. But the classical cost of simulating that quantum computation scales roughly exponentially with the volume. And so, as a function of time, the cost of simulating the quantum computer is growing doubly exponentially. So from that point of view, the quantum computer is taking off like a rocket, poised to surpass its classical competition, but it doesn't exactly tell us when we're going to be able to run interesting applications. So what are we going to do with these NISQ processors? There's an emerging paradigm of what we might try to do, namely hybrid quantum classical methods for solving optimization problems, where we would execute some reasonable sized quantum circuit, measure the qubits, feed those measurement outcomes to a classical computer, which would return instructions about how to slightly modify the quantum circuit, and then we would repeat that cycle with the goal of optimizing some cost function. As I've said, we don't expect quantum computers to be able to solve exactly worst case instances of NP-hard problems, but they might be able to find better approximate solutions or find them faster, at least that's the hope. And when we apply this method to classical optimization problems, it usually goes by the name QAOA, and when we apply it to quantum problems, like finding low energy eigenstates of a Hamiltonian, we call it VQE, but it's essentially the same idea. So should we expect this type of method to actually outperform classical computers in the relatively near term for problems that we care about? I don't know. But we should try it and see how well it works and experiment and try to improve the method, quoting Eddie. It's a lot to ask because these classical algorithms are pretty good and people have been improving them over decades. And meanwhile, the NISQ processor coming right out of the box isn't exactly expected to win the race right off the bat. Now, one thing that we worry about is that the classical side of this routine can be very computationally demanding. And naively, you might expect that we have to increase the number of variational parameters that we're optimizing over on the classical side as we increase the size of the quantum instance, and that makes that classical problem quite challenging. So what are we going to do about that? Well, one idea, which I think is just based on numerical evidence from this Google group studying MaxCut, is they claim in numerically simulating QAOA on a classical computer that when they fix the parameters for small instances, that gives them a good starting point for looking for optimal parameters for larger instances. I'm not sure why that's true, but they claim there's evidence for that. It may be that we should confine our attention, or at least focus our attention on cases where there's enough symmetry, where we plausibly won't need a great number of variational parameters to get good answers, for example, in translation invariant quantum systems. But what kind of looms over the subject is we don't have a very persuasive theoretical argument why this type of quantum method should outperform classical methods, as Hastings recently articulated. Now, if you want a little bit of optimism to brighten your day, you can talk to Peter Shor. He's an optimistic guy. And he likes to point out that there are many cases in the history of classical computing when there were algorithms which performed quite well, but where theorists were not able in advance to predict or explain that they would work well. And a current example of that is deep learning, which is having a big impact on the world, but we still have a very limited theoretical understanding of why these classical networks can be trained efficiently for many interesting examples. And so maybe it'll be like that with near-term quantum algorithms. We'll fool around, we'll experiment, and we'll discover applications which we can't initially explain why they work as well as they do. But because we're limited by the noise to relatively small circuits, it's likely to take a vibrant dialogue between the application users and the quantum algorithm experts to find useful applications in the near term. So how should we discover applications? It's often a good idea to go to Scott for wisdom. I heard him say this at a recent meeting, so I wrote it down. Instead of thinking of a hard problem and asking how to speed it up, ask what quantum computers are good at and build an application from that. And it was in that spirit that Scott came up with the idea of generating certified randomness with a NISQ device. Well, the idea is that once we have a sufficiently complex NISQ device, a client can send instructions to the quantum server to execute a certain quantum circuit and read it out and demand that the response comes so quickly that it couldn't have been produced by a classical computer. And then we can argue that there must have been a lot of entropy generated by that quantum computation, which we can then extract to get randomness, which we believe is really independent of the rest of the world. And there are a lot of interesting open questions about this, which should still be studied. And I guess the other application, which is kind of in the same spirit, is quantum dynamics, as Feynman initially envisioned, that if we want to take advantage of what the quantum computer is good at, we should study the problem of how quantum systems evolve in time. But it's a good question. What else fits into this category of using what the quantum computer is good at and building applications from that? Another way to inspire applications is to offer money, like a prize for a demonstration of quantum advantage which has a significant economic impact or societal value. And that would be judged by a carefully chosen committee of wise men and women, whether that criteria is satisfied. And you might think this is sort of a, if you're a cynic, kind of a shameless publicity stunt. But actually, the philosophy of it kind of interests me, which is, here we have this billion-dollar quantum market, so there's plenty of incentive to come up with applications. Everybody wants them. So why should you even bother to offer $1 million, which is, peanuts in comparison? But human nature being what it is, it does perhaps provide a incentive for some people to focus on the issue. I was talking to Peter Love about this recently, and he pointed out to me that there's been discussion for some time about how we could potentially use a market to reach judgments about what problems or instances of problems are hard by buying and selling tokens or options or setting up a derivatives market. And you can imagine variants on that idea which would price potential societal value and potential quantum advantage compared to classical algorithms. And in a way we have that already because we have a quantum market, not to mention the incentives that are baked into academia. But it's kind of interesting to think about if you were trying to design that market to enhance the probability of discovering important applications, whether there are mechanisms to build in that aren't currently there. I thought from time to time that we ought to have a quantum algorithms petting zoo inspired by quantum algorithm zoo, that is, with a focus on the problems that potentially could run as NISQ applications. I'm not sure what the criterion should be for enrollment in the zoo, but I would put the bar pretty low. It would be nice to have some clearinghouse of potential applications that we can build and consult in seeking important applications. And of course, meetings are important too. And it's particularly useful to have encouraged interactions among the quantumists with domain experts in optimization and chemistry and so on, and the eventual end users. Well, because I like oxymorons, I like what Jordan said about quantum machine learning. It's overhyped but underestimated. And I kind of see what he means. It's natural to ask what happens when we put quantum information processing and machine learning together. It may be that for some applications we can more efficiently train a quantum network. We don't really know whether that's true, but we can try it and see how well it works. Part of the reason for hopefulness about quantum machine learning comes from the idea of QRAM, that in principle I can very succinctly encode a large amount of classical data with an exponential savings in space in a set of qubits. But the applications or proposed ones of QRAM to machine learning problems often run into input-output bottlenecks, namely, if I have classical data and I need to load it into QRAM, that can be quite slow, nullifying a potential quantum advantage. And the output from the network will be a quantum state, so we can only, in each shot, collect a limited amount of information from it by measuring it. So it might be more natural in seeking quantum advantage in machine learning to think about quantum machine learning as a task in which both the input and the output are quantum states, which we could use to learn how to better characterize or control quantum systems. It makes sense that if there's going to be a quantum advantage in machine learning, if we're trying to, by training, learn about some probability distribution, the quantum advantage might be there if quantum entanglement underlies that distribution. So things that we might think about are, for example, we heard about using quantum error correction in sensing this morning from Paula. The general task is to find entangled multi-sensor states which provide some suppression of the noise without killing the signal. And quantum machine learning might be a method well suited for that kind of task. A good slogan for us is recognizing phases is harder than recognizing faces. In the case where the phase is topological and there's no local order parameter, and a quantum network, and this has been discussed by a number of people lately, might be well suited for identifying quantum phases. There's been a lot of discussion of using classical machine learning with the input some succinct classical description of a quantum state for classifying phases, but it might also be a good task for a quantum network where we can think of each phase having some representative model, like an exactly solvable model, and another state in that phase is that reference state, but with some noise attached to it, and the task of the network is to try to get rid of the noise through a sequence of coarse graining steps and error correction steps. Another thing that is worth considering is using quantum machine learning for the purpose of finding better codes and decoding methods for physical noise models in the lab, in particular for correlated noise. And because there's a lot of interest now in classical machine learning applied to chemical discovery, and also a lot of interest in the applications of quantum computing to chemistry, there might be a sweet spot where relatively near-term quantum machine learning can lead us to new discoveries in chemistry. I think in general, in both the quantum and the classical setting, there's a lot more that we might be able to do by thinking about machine learning from the point of view of renormalization group and error correction to understand the applications that work and find new ones. So the problem that we think quantum computers are especially well suited for is quantum simulation. We think simulating dynamics is particularly hard because people have tried to do it and are very bad at it. Quantum computers will be able to do simulations of quantum systems, and the potential applications could have a profound impact eventually, though perhaps not in the NISQ era, on human health and agriculture and the sustainability of the planet and so on. Probably those aren't going to be realized, at least not to that extent in the NISQ era. And because classical computers are particularly bad at simulating dynamics, that seems to be a great opportunity for quantum advantage. We might think of it this way, that back in the 60s and 70s, when people started to simulate nonlinear classical systems using classical computers, that greatly advanced our understanding of chaos in classical dynamical systems. And as of now, we don't really know very much about quantum chaos, but in quantum simulations, we might be able to learn about it relatively soon. Now, when I've made this argument that quantum simulation is the natural place to look for quantum advantage, sometimes people push back, like Frank Verstrada said this to me. Well, quantum dynamics isn't interesting at all because there are two kinds of systems. There are the localized systems, and they're not very highly entangled, and they equilibrate very, very slowly, and they might be easy to simulate classically, and they don't do much. And on the other hand, there are the strongly chaotic systems, and they converge to thermal equilibrium very quickly. We can't simulate that process because entanglement grows very quickly, but on the other hand, nothing interesting happens. They just converge to thermal equilibrium, and that's it. And I think the right response is, you can get interesting answers, but you have to ask interesting questions. And this is fun for theorists because it's inviting us to think like experimental physicists who have to deal with the question, I have certain capabilities in the laboratory, and how can I use them to make an interesting discovery. And I think there are a lot of situations where the classical simulation is hard because entanglement grows quickly, but would not be subject to the second half of Estrada's objection. One thing I've been interested in for a while, although it's not necessarily going to be a NISQ application, is applying quantum simulation to strongly coupled quantum field theory, where, for example, if you wanted to study a high-energy collision, which generates a large amount of entanglement, something interesting is happening that you might be able or want to characterize, but it's hard to simulate classically. Now, we can do either digital or analog quantum simulation. By an analog quantum simulator, we mean some system whose Hamiltonian we can control pretty well, which behaves like some quantum system that we're interested in studying or simulating. Whereas by a digital quantum computer or quantum simulator, we mean a general purpose quantum computer, which we can use to simulate any physical system of interest when we suitably program it. Now, analog quantum simulation is an activity which has been very active for over 15 years. Digital quantum simulation is just getting started. Some of the same experimental platforms, though, can be used for both purposes. Now, analog simulators ultimately are limited because we have imperfect control of the Hamiltonian and limited ability to control the noise. They're best suited for studying properties which are robust with respect to such noise sources. Eventually, digital quantum computing will overcome that limitation because we can error correct them, but that's not going to happen probably for a long time. So in the near term, analog quantum simulators offer a lot of potential for teaching us about new physical phenomena. So we should be asking, what are the hard problems that we can solve with analog simulators, even when we have imperfect control? And in the NISQ era, is there really a point to doing digital quantum simulation at all? In particular, for the purpose of simulating time evolution, well, that requires rather deep circuits by the methods that we know about. And so it might not be possible to do it with reasonable accuracy using NISQ devices. But digital has advantages. It gives us more flexibility in the Hamiltonians that we can study and in the types of initial states we can prepare. It gives us opportunities for hybrid methods where some of the load is carried classically. For example, using a classical computer to find a succinct description like a tensor network description, or maybe some kind of classical network description of an initial quantum state, which can then be compiled as a quantum circuit, which we can load into a general purpose quantum computer and then study or evolve. So I think there is a point to doing digital simulation with NISQ devices, but a lot of what we'll learn will be not necessarily deep properties of the physical systems that we're studying, but we'll be laying the foundations for doing more reliable simulations in the future where we really will see a substantial payoff in our understanding of fundamental physical science. And actually, you could say a similar thing about almost all NISQ applications, that we should think of them as sort of setting the stage for more useful applications which may come later. Incidentally, I mean, analog quantum simulators can do some rather amazing things, and arguably they're already being used to study highly correlated phenomena in many particle systems, which are quite hard to simulate on classical computers. And I just gave a couple of examples here. Now, I assume Misha is going to talk about this, but I wanted to highlight it as an example from which we should take some encouragement. Simulation done by his group of quantum dynamics in a simulator with 51 Rydberg atoms. So as I already alluded to earlier, we tend to think that there are two generic ways in which physical systems which are closed can converge to equilibrium. We can have many body localization where perhaps due to strong disorder, the system is not so highly entangled and thermalizes very slowly, but there can also be strongly chaotic systems which converge to equilibrium very quickly. And what was found in this simulation is a kind of intermediate case regime in the phase diagram where both types of states coexist, where some of the states thermalize quickly and some take much longer to thermalize. And that's quite interesting and maybe a signature of a new class of quantum matter far from equilibrium, which has been called a quantum many-body scar state, which just means that there are atypical, only slightly entangled non-thermal eigenstates in a system which is non-integrable and also has thermal states. And it's not clear at this point, at least to me, whether this involves some kind of fine-tuning of the Hamiltonian or how generic a phenomenon it is. But I think the good news is, in this, one of the earliest simulations to study quantum dynamics in a regime which is not so easy to simulate, classically a new phenomenon was found. And I assume Peter is going to talk about this tomorrow, but I wanted to highlight it also as sort of the state of the art of variational computations using quantum platforms. You could view this as a kind of intermediate case between digital and analog. It's an analog system with some digital controls. In this case, it's an ion trap in an experiment done by Rainer Bloch's group at Innsbruck. And as we heard from Chris, the ion trap has its own native Hamiltonian, but that Hamiltonian is tunable. So in preparing a quantum state, we can start with some initial state, evolve according to some specified Hamiltonian for a certain amount of time, rapidly switch to a new Hamiltonian and evolve for some amount of time, and so on with some number of steps, which is experimentally feasible, and then treat the parameters in that protocol as variational parameters. And even if we can't control the Hamiltonian very precisely, as long as the control errors are reproducible, that isn't an obstacle to using this method in variational calculations. And that group used it to study the low energy states of electrodynamics in one dimension. It was a 20-qubit simulation, and they got results which were in good agreement with exact diagonalization, which can be done for a system which is that small. And they also had this nice feature that there's some self-verification built in to the protocol. They can estimate, because for this system, the expectation value of the Hamiltonian minus some specified constant squared is just a sum of Pauli operators for a state prepared in this way with fixed values of the parameters. They can measure all those expectation values of Pauli operators by running many times, and therefore estimate the expectation value of this quantity in that state. And when E is actually an energy eigenvalue, that should be consistent with 0. And so we have a way of checking that we're getting a state that behaves like an energy eigenstate. Now, this was done with 20 ions. Probably it could be done with more. And what's encouraging in this case is there doesn't seem to be any sign of decoherence being a limitation on the reliability of the device. But it is running into this problem that the classical side of the loop is pretty demanding, and a lot of the effort in doing this calculation was on that classical side. There's one other thing that I wanted to highlight, which is a recent theoretical development, just as an example of how there may be other methods apart from QA-OA, VQE, for using relatively low-depth circuits for quantum problems. And maybe evading that problem that the classical loop is so difficult. In simulations on classical computers of quantum systems, imaginary time evolution is often used. That's a relatively efficient way of preparing low energy states of the system. And we know how to simulate such non-unitary operators on a quantum computer, but it's very expensive because we do it by introducing ancilla qubits and measuring them and post-selecting. But in this recent paper by Garnet Chan and collaborators, they proposed a more efficient way of applying contractive math like this one to a particular input state. We don't have to simulate the operator, only its action on a particular state. And through a combination of state tomography and solving some linear equations, which is classically pretty easy, one can find the right unitary that does the job up to a rescaling. And the circuit that's involved is relatively low depth compared to some other non-NISQ quantum simulation algorithms. At least it seems to work okay as long as we don't have a divergent correlation length, in which case the depth of the circuit that we need to get good accuracy blows up. So I'm not really sure how well this is going to work in practice, but I'm just pointing to it as an example of how we need to continue to think of new ideas for using relatively low depth circuits for studying quantum problems. Now these NISQ era quantum devices are not going to have error correction, and as I've been emphasizing, the noise puts a limitation on them. We understand that the ultimate solution to that will be quantum error correction, but there's very high overhead costs, and how high that cost is depends on the quality of the hardware that we use and the algorithm that we run. A recent estimate is that if we have a gate error rate of 10 to the minus 3 for 2-qubit gates, we need 20 million physical qubits to break RSA 2048 running Shor's algorithm. So if we're going to get into that scalable regime, we have a very daunting quantum chasm to cross from where we expect to be in the next few years with the order 100 qubits or so, or maybe a few hundred, and where we want to go, which is millions of physical qubits. And so the mainstream users who are eagerly awaiting quantum computers for solving their problems may have to be patient. But meanwhile, having the advances that we need to bring fault-tolerant quantum computing closer to realization are continuing to be very important, and it's a combination of many things that are needed. Certainly having better 2-qubit gates will help a lot, as well as theoretical ideas about doing error correction with lower overhead and better design of algorithms and so on. Now, what about the near term? In the long run, we'll have quantum error correcting codes, and we will have fault-tolerant protocols. In the NISQ era, at least to begin with, we'll be trying protocols that aren't really making use of error correction at all. What should come in between? Well, the problem is, naively, if you have a generic circuit with G gates, you'll need an error per gate scaling like 1 over G to have a reasonable chance of getting the right answer. That's assuming that the answer is sensitive to a fault at any circuit location. But that isn't always necessarily the case, depending on the problem that we're trying to solve. If we, in some physics simulation, want to measure few-point correlation functions, then we might be able to tolerate some constant probability of error per qubit. And for some of the methods that have been proposed for NISQ era exploration of low-energy quantum states, the quantum circuits that prepare the states have some built-in error resilience so that faults early in the circuit have an effect that decays away at a later time. Other ideas that have been suggested are extrapolating to the zero noise limit. For example, we can vary the amount of time over which we execute a quantum gate, and therefore adjust the noise in the gate, and then from results with various values of the noise strength, try to extrapolate to the limit of zero noise, and that method is already being used in some of the early NISQ simulations. And there are other ideas about how we might use resampling methods to get estimates at the expectation values of the observable that we're trying to measure without just doing a naive averaging of all the outcomes. We need more ideas like that. So I think the first event like this one that I remember attending was in 2013 at IBM. It was called What Do We Do with a Small Quantum Computer? And one of the answers that some of us gave at the time is we should be using it to learn how to build a big quantum computer. And I think that's still a good answer, not the only answer, but one of the good answers. And for those of us who are already working on quantum error correction over 20 years ago, it's kind of exciting to think that we'll really be doing quantum error correction in a serious way in the lab during the NISQ era. But we'll be doing it, of course, initially at a rather small scale, so you can ask whether we really learn interesting things from that. I think we could learn a lot of interesting things. One of the things we can get better at is understanding how to correct and mitigate leakage. There's a lot of reason to worry about crosstalk, and we need methods for characterizing it better and understanding how to mitigate it, either by compiling our algorithms suitably or by using coding methods that are well suited for dealing with correlated noise. There are a lot of methods that have been proposed for tailoring the noise or for engineering dissipation so as to provide some at least partial error correction, and testing how well those methods work in real devices is sure to be instructive. Doing logical benchmarking, that is, measuring error rates of logical gates, will be a good way of testing reliability of NISQ scale systems and may also teach us things about how well error correction works in the real world. At least initially, we can do what I'll call post-selected fault tolerance, that is, use error detecting codes instead of error correcting codes. That doesn't scale well, but it could give us some useful information about the nature of correlated noise and the things that we can do to deal with it. There are some clever ideas that have been proposed for diagnosing when errors produce, faults produce errors that spread badly, that propagate badly, to lower the cost in ancilla qubits of fault-tolerant protocols. And those will be interesting to try out and study, though it's not clear how scalable they are. But I think it's a real adventure to seek the eternal qubit, having qubits which, by means of quantum error correction, have a very long lifetime compared to the natural lifetime in the quantum device, will be a real milestone for our field. And in not too many years, we may have a lot of encouragement, or possibly not, concerning the prospects for scalability using the quantum error correction tools that we know about. And we also have good prospects for improving them through experimentation. And of course, we all want better gates. And the ongoing efforts, for example, to develop topological qubits or other methods for controlling noise at the hardware level continue to be very important. Okay, so let me sum up. We're entering the NISQ era, and we're all eager to see whether NISQ devices will be able to outperform our best classical computers. That's possible, but we don't really know for sure whether it's going to happen. We will be able to experiment with and test the hybrid quantum classical methods that have been suggested for solving optimization problems. We should keep noise resilience in mind in designing our near-term applications. Quantum dynamics seems to be a particularly interesting target for quantum advantage because it's so hard to simulate in highly entangled systems using classical computers. By fooling around with our NISQ devices, we may have opportunities to discover new applications that work better than theorists can initially explain. We shouldn't expect NISQ to change the world. Really, the goal should be to pave the way for the bigger payoffs that we'll find with future devices. There's a very strong incentive to continue lowering the 2-qubit gate error rates. In the NISQ era, that will mean we'll be able to study and execute deeper circuits, and in the longer run, it will mean a lower overhead cost for fault-tolerant quantum computing. That quest for fault-tolerant quantum computing shouldn't be far from our thoughts. I think it's the key to our quantum future, and progress towards fault-tolerant quantum computing should continue to be a high priority for quantum technologists. But in short, these are exciting times, and I think we have a lot to look forward to in the next few years and beyond. So thank you very much.
Thanks, John, for that inspiring talk, and I think we have time for a few questions.
So you talked about, first you compared, analog versus digital simulation of quantum states, and then you talked later about sort of a programmable analog computer, and I was wondering to what extent advances in digital computers can help us do analog simulations. For example, if IonQ was able to build a 1,000 qubit device next year, would that be something that we could use for analog simulations, or is the gap just too big? And likewise, I guess, for superconducting qubits.
Well, I mean, I'm sure they'd be able to use it to do interesting things. So the type of simulation I described, which was of finding low energy states, in particular the ground state of a one-dimensional system, I think is probably not a very promising path to quantum advantage because we have such good classical methods for doing one-dimensional physics like density matrix renormalization group methods. 2 dimensions and beyond are much more interesting. Now, in fact, in the case, because of the all-to-all connectivity of an ion trap, the geometry of the system was not very important in that simulation that I described using 20 ions. And as a matter of fact, the way they do it is they integrate out the photon from one-dimensional electrodynamics, and then they get a kind of non-local spin model, which is what they study. But with 20 or 50 qubits, you wouldn't be able to study a 2-dimensional system of a size which is probably going to be very physically revealing. With 1,000, then maybe it starts to get very interesting with 1,000. I think the other thing is that dynamics, as I said, may be the more promising path towards quantum advantage. And with a 1,000 ion trap with all-to-all connectivity, I think there are studies of dynamics that would be very interesting to understand in a sharper, more detailed way than we can with current experiments. For example, the scrambling behavior of strongly chaotic systems.
Another question here in the back.
I was going to ask you if you could elaborate a little bit on quantum dynamics, how it can be leveraged, and I'm wondering how periodically driven systems might play into quantum computing. Do you have any thoughts on that?
So I guess the first part of the question is, what is it about quantum dynamics that's so interesting? And the second part is, are there particularly interesting opportunities in the case of periodically driven systems? Well, in fact, I think the answer to the second question is yes. And in general, the types of quantum phenomena that occur in driven systems that are highly entangled, we have very poor theoretical control over. So, and there have already been very interesting experiments studying phenomena like time crystals in periodically driven systems. And there will be opportunities to explore that much more accurately and in more detail, I hope, in the NISQ era. As far as what are we going to learn from quantum dynamics? Like I said, I don't know that it's really going to be a NISQ era application. Well, let me put it this way. There are lots of dynamical phenomena that we would like to study in correlated systems, including in condensed matter. When you have a strongly correlated system, just studying properties like transport and conductivity and viscosity and so on, analytically extremely hard, and maybe most naturally studied in a dynamical simulation rather than a static one. So I think there will be lots of opportunities like that. I'm interested in things like what happens in quantum field theories that are far from equilibrium, and I think we can do baby versions of those types of simulations in the NISQ era. I don't know if we'll really see big physics impact from that, but we'll be setting the stage for impact later on.
Maybe we have time for one more quick question if there is one, while Dave gets set up.
So I don't know what your favorite metric is, but there's this quantum volume versus the supremacy versus you mentioned quantum advantage. Sort of what do you look at when you were think of a metric for what we should be shooting for.
Yeah, so the question was about what kind of metric we should use as far as what we should be shooting for. And you mentioned specifically quantum volume, which I won't explain exactly what that is, but it's, what you might naively expect, it's a measure of a combination of the width, the number of qubits, and the depth of the circuit. And it's intended to characterize roughly the classical hardness of doing the simulation. But I think really the right way to think about it is in an application context. That if there's some application that I'm really interested in, the question is, how far do we have to go with the quantum device so that we're really doing something which is beyond what we can simulate classically? I don't really think, it's useful to talk about quantum volume and other such general purpose measures, but it tells us about the cost of simulating generic circuits, not necessarily ones we care about in applications.
Okay, thanks. Let's thank John again.
That's yours. Got the wrong slides up there. Sorry about that.
Okay, so next it's a pleasure to introduce another luminary of the field, Dave Bacon from Google, who's going to tell us about enlarging the IS.
Okay, great. My mic's working. We'll see if this back and forth thing's working as well. So my name's Dave Bacon, a software engineer at Google. And I chose the title Enlarging the IS in NISQ. Those who are at 2QC know that there are other approaches, like we can, remove the Q from machine learning, which is, what the first talk of the day for TQC was. But I thought this was a great title for the talk because, first of all, I knew I could achieve it. And I've now done that. So I enlarged the IS, and now you guys can all go home. We're in an interesting era. I left the field of quantum computing about 8 years ago. Went off, became a software engineer, and now I'm sort of come back and see it with a new set of eyes. And when I left, the only way you could get any traction with any of your ideas as a theorist or somebody who was interested in actual quantum computers was, to go find your experiment friend and beg. You basically had to camp out in their lab and be in between them and their machine to get them to do anything for you, right? And that's because they were just trying to get the basic single qubit and 2 qubit gates working, right? And as an engineer, I now realize how distracting theorists are when you're trying to get things done. And so they were, really focused on that. And today we're in an exciting new era, right? And a lot of credit to IBM and Rigetti in particular, who've gotten out with their systems, being accessible to people. Right now, any dog with some laboratory equipment can think of their idea and try to go run it, right? It should be extremely exciting. If I was a 13-year-old geek, which I once was, I would be extremely excited about this, right? And I think this is only going to generate more excitement as we get more performant devices on the cloud systems, and we have more and more access to this. Okay, so I want to talk about this perspective of NISQ devices. What are they, and sort of how do I think about them? This is the picture I always have in my head of I always have this picture in my head that things are extremely complicated, and I try to draw a picture of what can we do with a quantum computer? And I always pull this calculation that was done in Nielsen and Chuang. That's how I can tell how old I am. I think I'm cited in it, so it's that's a super old man, right? But it talks about you're trying to cover all of your gates that you can possibly do, so SU2 to the n qubits, and you're trying to cover that with patches of size epsilon. So you're thinking about the state space you can get to, right? And that scales doubly exponentially in n, right? And if you just look at the number of gates you can do, so you sort of think about, most systems start out in some fiducial state. Almost everybody starts out in their computational zero state. And then you just start thinking about you're expanding across this thing. What could you ever possibly reach, right? And so you look at, you have n qubits, and then you have some gate set that has some size, some expressivity of the different numbers of gates you can do. And then there's some fudge factor, which has to do with the geometry and the parallelism and the gate fan-in and exactly what you can do with your device. And you do that, you look at that, and the size of that grows as, into the number of gates. So it grows fast because the number of gates can grow like n, right? So it's growing pretty fast, but it's not growing fast enough, right? And if you calculate, the number of gates to reach all of these things with a given epsilon, you realize that there's a 2 to the n there, right? And this is just this thing that there are always states that we're never going to get to, right? For larger and larger n, right? There are very lonely states. They will never be reached in our lifetime. But the reason I like this picture is because now we sort of think about like what is the space that we're getting to, right? And the space of reachable states may not be the right dynamic, but it's at least one picture of what that sort of looks like as a cartoon. And what I want to emphasize, and I think is true, and I actually think is exciting, I think it's a positive, not a negative, and it's coming sort of also from Chris's talk this morning. I think it really ties in with it. Is that I think these regions that we're going to be reaching in the short term they're very different depending on the actual architecture of what your quantum computer does. And to me, that's actually exciting because I think I suspect they're going to be in some ways very incommensurate NISQ devices. And so we should be thinking about all of them and sort of embracing the diversity of the different approaches, right? And each of these different approaches will have, different geometry. So for example, all-to-all ion trap connectivities. They'll have different fundamental gate sets. They'll have different gate set speeds. They'll have different gate repetition rates. All these things are going to differ between these devices and are going to influence the types of algorithms we should be thinking about. So I just want to show you at Google, one of the things that this has sort of helped our thinking is sort of like that it is important to think about these in the NISQ era. I think it's actually interesting to also sort of think about the idea that the tool set that we want for NISQ may be slightly different than the tool set we want for the fault-tolerant quantum computation. In fault-tolerant quantum computation, you might want to focus on just one gate and perfecting it, right? Like you've got your C0 and that's what you really care about, or your few sets of gates that you care about. Whereas NISQ, we might actually want way more, interesting dynamics, and that sort of changes the design space for engineering these computers. So I'll show you an example of that in just a second. Okay, so what are we up against? This is like my sobering thing. I was like, okay, what can I do with a NISQ computer? Let's first talk about like if I want to do an extremely high precision quantum experiment, right? So let's say I have 2 qubits and there's let's say the 2 qubit gate is my limiting operation here. Let's say I can do that with 3 nines, right? Like that's pretty awesome. Superconducting people would be ecstatic about that. Ion trap people would be like, oh, we do that all the time. But that's a very good number, right? Like, and people are very happy when they choose 1 in 1,000, right? And then you sort of look at the past light cone of that on, say, a grid. So this is thinking about maybe the grid type architectures, right? So if I sort of do one step back in time, sort of like the past light cone, right? I can count I now have more qubits. It's bigger, right? And the number of 2 qubit gates is now also bigger. And already when I do that, I'm down to 1%, right? Because I have 8 2 qubit gates that I have to do that full light cone, including the first one there. Right? And so just even that small depth, you're starting to get down if you really want to do what I call like ultra precise experiments where you're caring about failing with 1 in 100 for your experiment, you're already like, oh, this is not so good. You go to the next level in the light cone, you're getting up to 18 qubits, number of qubits is growing fairly fastly, and you're down to 4% error or 3.5% error. And then once you go to the next step, you're already down to sort of 10%. So you shouldn't be thinking about these devices in the way of like, that I will get the very precise output that I'm doing in this sort of regime, right? Like we can do very small versions of those experiments, but that's not really I think the right model. The other model that I use when I talk to people about NISQ is I try to say, well, what are you trying to do? Well, you're trying to get maybe any signal at all out of your experiment, right? And for us, for example, in superconducting qubits, if you have 3 nines of fidelity for your 2 qubit gates, by the way, did anybody go to the 2 nines Mexican restaurant for lunch? There's a restaurant around here which is actually called like 99% authentic, which I think is awesome. 2 nines of authenticity for Mexican food is good for me. I'm fine with that. So you have 3 nines of your fidelity of this, and you're doing something that's depth D. and you're doing it on a 2D lattice, and so you have to interact each one with its neighbor to the right and its neighbor down. And so you can sort of look at that fidelity. So now I'm not thinking about light cone, I'm just thinking about the sort of full fidelity of this. But now I have a measurement at the end, and in the measurement I may want to measure some observable, like ZZ, right? That's typically what happens in a lot of variational algorithms. Let's say it's just a two-body one, so let's say I had a 1% error in my measurement. If I have a 1% measurement in my error, I'm never going to see anything better than that, right, in my measurement outcome. And so if I need to repeat a lot of samples, right? So I repeat a lot of samples, and if I go more than 100,000, so 10 to the 4, it doesn't really increase my signal anymore because I'm already at the noise level of my measurements, right? And so you can sort of calculate where does that cross? Where is it that possible if you could see anything? And so, for 9 for n equals 9, it's about depth 89. It's pretty good, right? But once you're getting up to say 54, it's down to depth 14. And so that's sort of the constrained space that I think about when thinking about these algorithms. Okay, so in that regime, so think about these numbers, right? Depth really matters. If I'm doing a 54-qubit machine, these numbers are totally taken at random, have nothing to do with Google's machines at all. So if you're doing that, you really, a factor of 2 makes a huge difference in your depth, right? And so in our designs of our quantum processors, and I talked about this at the industry meeting for those of you, industry session, those of you who stayed, it's influenced our design in a couple ways. We've now designed a system where we have this 2-dimensional coupler that is, we have a 2D design, a 2D grid, and we have a tunable coupler. And that basically means we have essentially an extra qubit in between our qubits that we can turn on and off or we can interact with by pulsing it, and it essentially has a 0 state that's off, right? So we can tune it in such a way that the qubits are not interacting with each other. Our previous gates from, say, the bristlecone device didn't have this type of coupler between them, and we had this issue that when you're doing your 2-qubit gates, you could only sort of do them in this staggered pattern here. If you're doing a 2-qubit gate, you couldn't do anything on the gate surrounding it in one sort of like cycle. But with these tunable ones, we can turn, and the essential reason for that is we have to park our frequencies on a plus or minus checkerboard. And because of that, we can sort of like get around this problem. We can actually not worry about that plus minus checkerboard in these tunable couplers, and we get a much higher parallelism. And if you work out what that actually has consequences for your actual NISQ type algorithms, it's a pretty big consequence. So that really does help you, right? Another thing that's important is that this coupler actually has a different natural gate set than our previous devices. In particular, the previous devices, the natural interaction was sort of phasing the 1-1 state. But these states with this pulsed interaction now do something we call the FSIM gate because it's really closely related to fermionic simulations when you're doing, say, a Jordan-Wigner in 1 dimension. So this is the FSIM gate, and it has this form of sort of xx plus yy, e to the I xx plus yy for some angle. So that's that middle angle rotation, sort of a I-swap like gate. And then another phase on the 1-1 state. And this space now is larger, and so if you're thinking about, when you think about compiling your circuits down, having sort of this, what you would say is, rank 2 in the Weil chamber, being able to explore that larger space will give you more expressive power in that amount of depth, right? And as a fault-tolerant person, I might not necessarily think this is a useful thing to have all of this. I really just want you to give me a really, really good seat phase, right? Or maybe a really, really good I-swap or square root of I-swap maybe, right? But, like, you want to focus on one particular one, which will happen when you're doing fault tolerance. But here, when you're trying to actually get as much as you can, you want this bigger Weil chamber, and you want to be able to get to as much as possible. Okay, so just to tell you this is not fiction, this is a plot that appeared in Charles Neal's talk at the APS March meeting, which is for an 18-qubit system that we built. And the color thing on the right is sort of what we call our cross-entropy benchmarking error. We use cross-entropy benchmarking to figure out what our error is. I won't go into the details of that, but it ends up, we get up something that's like 0.6 median error for these 2-qubit gates. So that's pretty good. These are really exciting gates, and I think we're going to get a lot of leverage out of having this big space and trying to get as much expressive power in that sphere as possible. Okay, so what I want to talk to you today about. So today I'm going to talk about things that I didn't do, which is awesome, but was done by people at Google. I'll talk a little bit about something that I am personally interested in, something to talk about, so we'll call that the bacon bit. Hopefully I'll get to the bacon bit. But I'm going to talk about work that was mostly done by Jared and Zhang. They're the primary doers of this, but also Ryan and Nicholas and Hartmut at Google. The good thing is I'm not on these papers, but I'm in the acknowledgement sections, which I always think about as like the John Preskill position. Like he's acknowledged in all of these papers, and I always think like it's a badge of honor. I think you may be the most acknowledged person in quantum computing. So, okay. So the question that sort of comes up when you start thinking about error mitigation, let's try to figure out what we can do to like increase the IS by mitigating our errors. The first thing you think is like, let's just do error correction, right? Because like we know this, it works, right? Well, it costs a lot, right? And there are other reasons you might think about, like in our current systems, why this is hard. Like a lot of the engineering going into doing, say, feedback that's fast enough, and doing your coding, and there's a lot of engineering challenges that go on there. And maybe your gain's not high enough. Maybe you're like right at that boundary of actually getting anything out of it. And if your gain is like, really not very good, and you like square it, it's like not very impressive, right? So you might be so close that you don't care about it. So let's just think about doing some sort of error correction, but not like like not doing the full error correction. Okay. So I'm going to get there. It'll take me just a second. It'll take a detour. Most of you know this detour. It's a great detour to see because this is sort of for me, the progress that's come in thinking about this story of variational quantum algorithms, right? So this is a picture of an experiment done in John Martinez's lab for doing the simulation of hydrogen, right? So it's a fairly basic experiment. You essentially have 2 qubits, and you're doing a variational algorithm on your Hamiltonian, which is the sum of all these terms. And there's the circuit on the bottom. And it's a very nice experiment, sort of the first proof of principle, or maybe not the first. I hate the word first because I don't really care who did the first thing. But it's a very nice experiment doing this proof that you can do these variational algorithms and do this feedback. Now, the interesting thing about this experiment for me is that there's this idea, and this sort of plays out in this experiment, that in these variational algorithms, you have different parameters in your circuit that you're optimizing. And if you try to calculate what these are from theory, you might get some answers and try those numbers, and you try those numbers, and they don't necessarily work as well as if you put it in a variational algorithm and try to find the optimal values. Right? This is because there are probably systematic effects or effects you don't understand that are going on. But the variational algorithm, if it's high enough precision, is very good at trying to narrow in on this. So the plot on the left is showing that it works. Ignore the PEA, the phase estimation algorithm, right? Showing sort of that it works. There's error you can see over on the left, and there's the error at the theoretical angle is all over the map, right? But the error at the experimental angle, where you're sort of closed loop doing the variational algorithm, is much, much better. Right? And this should give us hope for these types of algorithms, and they sort of naturally try to get themselves into the good spot. It should also make you depressed as a theorist. You're like, oh, my calculation's horrible, right? Like, look at all that. It's like noise. But it may be that that's actually really good, right? There'll be a play where theory actually tries to understand better why that is so bad, which will then influence like our understanding of these algorithms. Okay, so the next step in the story in variational algorithms is to talk about this, what people call the quantum subspace expansion. It's a very nice sort of natural idea, which is that in variational algorithms, for a lot of problems, we're trying to find the ground state of some Hamiltonian, right? So we have some initial state, we have an ansatz, a circuit that's parameterized, and at the very end, we're hopefully producing the ground state. But we might also want to get to the excited state, right? And we'd like to understand that. And so the idea here is fairly straightforward. What you do is you just, let's say psi 0 is what you've got for minimizing it. Now you just look at that phi 0 operated on by, say, different Pauli operators. So different operators or different things that are, you think, likely to get you into that excited state. And usually from physics, you have some idea about what those things should be. And this gives you a new subspace, right? And you can look on this subspace and then sort of, in some sense, recast the problem of what you're doing. And you're trying to solve sort of this generalized eigenvalue problem, right? Where you have, those subspaces that you go from the different Pauli things might have overlap. So there's some sort of metric that is you're walking around this. So that's sort of captured by this Sij overlap, right? And then the Hij is you're measuring sort of the Hamiltonian, right, in this new subspace that you're working over. And you're trying to now essentially recalculate, find the expansion in this subspace, right, that gives you, that solves these eigenvalues, and in some sense is now giving you a new improved ground state. It also gives you an excited state, right? Because we now have a space outside of there, and we can just do, right? We're doing a bunch of experiments here to measure. We're gonna, I think it's on my next slide. Oops. We're going to, you know, we have these Hamiltonian, we have these H sub i's. These are going to correspond to things we can measure in the lab, and then we're going to use this to then solve that eigenvalue equation. So of course, it doesn't scale if you have a huge amount of these, but doing a few of them is actually really useful. In particular, one of the most important things is suppose that you have your Hamiltonian written down as a sum of Pauli operators, right? And then you're looking at, say, these Sij and Hij things. Well, what are they? Psi 0 remembers our ansatz that we've produced. So we produce this state after our parameterized evolution, right? Well, what are these things? These are just expectations of Pauli operators, right? Because, or let's say the ones I'm using in my subspace for Pauli as well. Just, I didn't say that, but that was my assumption on the previous slide, right? These things are all just sums over Pauli expectation values. So again, just like in the variational algorithm where we calculate, you know, where we experimentally determine the expectation value of Z1, Z2, now we might have to do things where we do, you know, Z1, Y2, right? Like that might be one of the things we have to calculate. But by just doing those extra measurements, right, we can calculate this new Hamiltonian. And this was done in an experiment, I believe that was done in Berkeley. And what's nice is you do see this improvement. That's the next slide. But you see that you get the excited states. You also get some really cool things that are coming from these spurious states, which are actually really interesting. But you actually get the excited spectrum of this. But more interestingly, you actually see this effect of the sort of surprise when they did this experiment in some sense, though there was some ideas about why this would be true, was that you do this and you get this new, this new energy for your ground state, right? Because you've added in these subspaces. And here what they do is they look at like different subspaces. So I, the one on the upper left, is like you just did the normal variational algorithm and you got that estimation. So that's the yellowish green, pukish green color up there. And then you start saying, well, what if I do some subspace expansion with different Pauli operators? And there's ones where they do single qubits and they add all of them into one batch. And you see that the error from this is not a thing that's hard to simulate. We see the error goes down because of this as we go into the subspace. So we do actually get sort of a better approximation. In fact, we get sometimes, they were able to get sometimes down what people call chemical accuracy, which I always take to mean what accuracy you would ask a chemist, and they'd say, oh, that accuracy. But anyways. Okay, so the thing that's interesting about this to me, from the perspective of like thinking about now error correction, is it's a kind of neat technique in that you get this state and then you're pretty sure it's not perfect and it's not the best absolute answer. But what you do is you just sort of like explore around the space, right, in this other subspace, and then work on that and sort of figure out what the thing you're diagonalizing looks like, and you can get sort of better estimates. Okay, so now I'm going to talk briefly about stabilizer codes. Luckily, like nowadays, like they teach stabilizer codes in Chris Ferry's books, right? Like How to Teach Your Baby Stabilizer Coding. I've read it, it's fascinating. This is the obligatory slide about stabilizer codes. Hopefully you know what a stabilizer code. There's a stabilizer group that has a set of generators. They all commute with each other. They all have eigenvalues plus or minus 1. Minus identities not in the group. You can define a code space as the common plus 1 eigenstates of all these operators, and then there are these logical operators that operate on our encoded qubits, and there can be k of them in this. Obligatory slide. Let me not connect to the network. Okay, so let's just do the simplest idea. Let's just say like, oh, let's work on an encoded space, right? Let's just see what happens when we do that. So what is that going to mean? Let's say we have some now logical operators. So we're going to work, we'll take a few qubits and we'll encode them into an error correcting code. And then we're working on some problem space, say for the variational algorithm. So we'll have a bunch of things that we've encoded, right? And so what we're going to do is we're going to, in the end, we're going to need to evolve according to that, prepare according to that, and then measure according to that observable, okay? So of course errors will occur. Measurement of the observable will be degraded. But let's just ignore that for a second and say, what if we just look at like one part of the encoded subspace, right? So let's just do this and see what happens. So what you're going to do is let's just say we prepared our state in this encoded space. Let's ignore how we got there for a second. Let's do our evolution in the encoded subspace, and then we're going to make measurements like in the variational algorithm, but now we're doing measurements of Pauli observables. So of course there will be errors in this system, and the system will be knocked out of that space. But we do know that likely that's not the most dominant thing to happen, right? Lowest order identity still occurs, and then with some probability we get some errors. So a natural thing to do, and it's always embarrassing to talk about any symmetrizing principles in front of Lorenzo Viola, is to just look at a subspace, right? Like that's been symmetrized over your code, right? So it's to do the projector onto that code space, right? So let's just look at what that is, and it's, you know, a kind of gnarly expression. You have your density matrix, and then you have the projector onto the subspace, and then your observable. Similarly, I'm going to renormalize it because I want to say, oh, I'm just going to look at what it is over this subspace, and I sort of know how much weight is in that subspace. So I need to renormalize it by this eta sub s. Now, the nice thing about this is it's just like the previous one, which is the previous subspace expansions, if you start thinking about it a little for a while, in the sense of when I do this calculation, I can expand my projectors over into the sum over the stabilizers. And now I have a bunch of poly things and then traces. I can move things around. You can rewrite this entirely in terms of the density matrix times, you know, whatever your expansion is for your logical operator you're measuring, right? There's an L sub I that's a logical operator, and then there's a stabilizer group element. And these are all, again, just poly strings, right? Strings of poly operators. And so that is just a measurement of a poly operator. And the idea from this paper is very simple. It's just when you're doing this, you can measure this to some precision, right? Just doing independent experiments. There's, you know, there's 2 to the n minus k of these terms, but we can just run, you know, 2 to the n minus k experiments and calculate these expectation values and add them up together. The same story holds for the normalization condition, right? Because it's just the projector onto the subspace, and so you can just shove that in there and see that it's just a bunch of terms like this. Okay, so that's okay. It's an interesting idea. It's likely to help you, but one of the problems with it, of course, is it doesn't scale, and you're also measuring a lot of stabilizer elements, right? So this is, you know, what we'd really like to do is measure all the stabilizer elements. So the thing that Jared and the team looked at that is kind of interesting is to try to look at how to do this with fewer measurements, right? So in particular, you want to sort of look at, your goal is in some sense to try to find something that's equivalent to minimizing what you could call a code Hamiltonian. Your code Hamiltonian is like, say, minus the sum of your generators, though it could be, have extra terms in it depending on your error correcting code, and you're trying to sort of like, want to get the system that's like kind of close to that. And so now you can look at smaller approximate projectors, where now you're looking at this P, which is a sum over terms that are now not across, say, the entire stabilizer group. So you can take away some of these terms. And going through the math, you can work out that you end up with, again, a generalized eigenvalue equation for this, which has these terms, which if you look at them are stabilizers or H code, which are also stabilizers. These, again, just turn into being measure the expectation of stabilizer operators over your code, okay? So this is an example of this that they ran for just the 5-qubit code. And so the important thing here is they sort of defined 2 versions of this. Well, there are 4 versions of this. There's the P sub L, so they projected on between either 3 or 4 of the stabilizer generators. Right, so the full one is L equals 4, that's the full projector. L equals 3 is you've taken away, like completely removed one of the generators. And then the more interesting thing, and this plot's kind of bad for showing it, is that they actually the star ones there, you can kind of see they're a little darker there, have one of those projectors, but they randomly removed 2 projectors and then used the quantum subspace expansion to actually, you know, find the right values of C sub G when you've removed that, and what ends up happening for your performance. So the performance here is they send it through a depolarizing channel with probability P, and there's the plot of the fidelity, there's the Baire rate, right, and then there's the actual physical rate. The Baire rate would be, you know, the physical rate would be, you know, what would just occur with a single qubit. Baire would be if you're encoded and you're, of course, you know, trying to keep the encoded information around, but just dissipates really quickly. And then there's these 2 levels. The L equals 3 is we've forgotten one of the generators. The L equals 4 is we've forgotten none of the generators. And then the star, did I flip it? I think I flipped no, I didn't. So the star makes it worse, right? The star means I removed 2 of the projectors, so it gets slightly worse. But notice that for the L equals 4 case here, right, you still get a sort of pseudo threshold type improvement by just removing some of those projectors. Okay, so just to summarize this part of the work, this is sort of I think the beginning of thinking about how to do simple error correcting type things without actually having to attach ANSLAs and trying to just get as much as you can without actually doing the fault-tolerant protocols. There are a lot of problems with this. Down at the bottom, how do we think about state preparation? We know in fault tolerance, errors spread badly. I think one of the reasons why I'm optimistic about this work is, there's some reasons later on, but I think one of the interesting things is in the variational algorithms, what we do see is that, the variational ansatz is actually pretty good at taking care of the systematic, say, over-under rotations that we have. And those tend to be a major source of our errors in our system. Even for the superconducting qubits, which don't have the infinite lifetimes of ions, that tends to be a very common error. And so we might be able to get to highly accurate state preparation with these sort of variational algorithms. And that might be less of a worry about getting into the encoded subspace. There's a bunch of extensions to this. One is I did a projector onto the code space, and I was looking at the code space, but of course you could also look at the aired space and think about the aired space plus correction. Again, that will just be sums of Pauli operators. You can play the same trick there. And then there's this idea that you don't have to actually measure all of them. Just stochastically sample or do some important sampling across this to try to actually just get a good estimate of what these observables are. And I don't think in the paper there's some arguments about why that might be good, but I don't think I have a great understanding about where the limits of that are, and I think that's an important open sort of direction. Okay, how am I doing for time? 10 minutes. Okay, great. So that's sort of the first step, I would say, in sort of just thinking about any bare bones amount of using error correction in these systems. There'll be an overhead associated with that. I'm not sure how big the overhead is in the sense like Chris said, it is increasingly easier to build larger and larger systems with more qubits. If you're, that's becoming increasingly true. In superconducting circuits, for us, the limiting factor, fabricating the thing is probably not the limiting factor. It has to do more with, wiring and maybe, things like, more subtle things like that, like, maybe you put too many wires and your dilution fridge can't hold it or something, right? Because it's too big. But that's the more limiting thing. So, but it's not unreasonable for us to think about more qubits at the expense of sort of doing these other interesting encodings. Okay, so finally I want to give an example of an error correcting code that's tailored to simulation. Because of course we're very interested in whether we can do quantum simulations for all the reasons that John talked about. So here's the obligatory Fermi-Hubbard model slide. So we have some fermions, and in particular we're thinking about this on a two-dimensional square lattice. And we're thinking about simulation algorithms where we may be trying to prepare some state, maybe an excited state, doing some evolution and some measurement. Doing this on NISQ devices in ways that are not easily simulated by a quantum computer is very challenging, but we might want to start pushing that regime as far as we can. Okay, so for these types of systems, so in particular I'm talking about two-dimensional lattice models, right? So I'm not talking about one-dimensional ones or ones with crazy all-to-all interactions like in chemistry. I'm talking about the cases where it's on a lattice and things are sort of hopping around on the lattice or have same site terms and then, that type of setup. One thing you might do for most, your most natural thing when you go back and read about fermion simulation algorithms, right? One of the first natural things to do is to use this Jordan-Wigner transform, which maps your fermions, right, onto your qubits. But if you do this for a two-dimensional system, you see it has some pretty gnarly problems, right? In particular, it has this problem that, the hopping between K2 and 7, which are nearest neighbor on your lattice, has the product of all these Z's on the, 3, 4, 5, 6, right? So it's this big, turns into this big clunky operator. Now, in chemistry, where you sort of have this problem, but you have sort of all-to-all in the fermions that you want to do, there's very nice work where you do swap network, these F-swap networks, and you have every qubit talk to every other qubit, but that tends to be, much more, you're now going into much higher depth. We'd like to do things without this really high depth. The good thing is that if you ask that question, there's an answer, because as everybody knows, there's a couple oracles you go to ask for. One of the oracles you go is ask Sergey and Bravi and Kitaev, and you see there's this beautiful super fast transform they have. So I don't want to dwell on this because it's not super important, because I just want to give you a flavor of the results. You have these fermions on a lattice. There's this trick that you do, that you look at Majorana fermions, and then you end up with these complete set of operators that sort of sit on vertices and edges that's sort of equivalent to these Majorana fermions. to the original fermion model that you're caring about. So you really just care about these two-body Majorana fermion operators. You define them on edges and vertices, and it's a nice model. So way back in 2002, which is before the Earth cooled, Sergey and Bravi came up with this transform. People call it the super fast transform, which I think is super awesome. And this operation maps those eta operations, the vertex operations, to sort of z's that go around on your edges, and then they map these sort of hopping-ish type things to x's as well as these z's that sort of go on neighboring vertices from which you're hopping. And there's some ordering that you have to do there. The other thing is that you have to employ this condition on this system in order for it to be simulating the fermions correctly, and that this is this condition that these eta, or xi, is that a xi? I always say eta. It's a xi, sorry. Around a loop have to be 1, and that turns out for the polycodes to be a stabilizer operation. So there's a stabilizer code in here. You would force the stabilizer code plus 1 eigenstate of all of these, and then you use these operations on that encoded space to do your fermion simulation. Recently, this was looked at by the authors down below, where they looked at this, and then it is a stabilizer code, so it's natural to ask the question, like, does it have any error correcting properties? And what they did is they were able to show a no-go theorem in the sense of if you want it to have distance 3, so it can correct 1 error, then if the vertex degree was less than or equal to 6 for your graph that you're working on, then there is no single qubit error correcting property of this code. Okay, that's kind of a depressing thing. You'd kind of like it to be able to at least correct 1 error. What was done in this work that I'm talking about today was that there was, for the square lattice, it turns out that if you properly choose the ordering in doing this, you end up with a stabilizer that can detect a single qubit error. And what's nice about that is the symmetrization procedures that I talked about beforehand are pretty okay with detection in the sense that, like, you're trying to have some weight in your code space. A single qubit error might take you out. You're going to get some signal out of that, right? So that was the first result. The other more interesting result, which I can't talk about because it's just like an amazing squid diagram, and if you want to have more information, you should talk to Zhang or to others who have worked on this. But there is actually a way to, they 4-color a square lattice, and then they come up with these crazy hopping operators. The dotted operators are like the vertex operators. The solid line ones with the X things are like the hopping type operators. And you can go through, and for each of these, you can come out with these different hopping operators and vertex operators, and then you put them together, and you get the stabilizers for these things, and you can show that this code actually does correct single qubit errors. So again, I'm happy to be back in quantum computing because it's an exciting time. I'm not so happy because I am not nearly as smart as the people who come up with these things, right? It's just like, where does this come from, right? So, but the end result is nice. We now have, a way to do fermion simulation. You have to measure these high weight operations to do error correction, but that's sort of, in the spirit of the previous discussion, it's sort of not an unreasonable thing to start trying to do. This transformation has some other important properties in terms of the size of the operators. It's slightly better than the Bravi-Kitaev superfast or the generalized version of that, but that's not that important. Okay, so again, the big part that's a problem here is these are big operators to measure. You'd like to combine this with subspace methods. This is clearly something you can start trying in the experiments that are coming up in the next few years. Okay, so I'll finish off here. I think this is the most interesting thing for me, which is that John always says this thing about we should use the small quantum computers to build the larger quantum computers. I actually think we should take this actually fairly seriously, in the sense of in quantum computing today, especially if we look at, say, Microsoft or in comparison to, say, INQ or Google, there's sort of these two big approaches. There's this approach that the superconducting people and the ion traps, it's just like we're just going to brute force our way to quantum error correction, right? Like we're going to engineer really good hardware. It's extremely hard to build these things, but we think we can get to error correction, and we're going to build that. On the other hand, we have the approach taken for people who are doing topological quantum computing, where we know that we think that there are these physical systems that have protected subspaces that are error correcting codes, and sort of energetics will keep us protected. right? But here the challenge is do you really know that your Hamiltonian that you have, that you're trying to engineer out of that, really does what you think it does? And is it a robust phase of matter that we can actually probe? And that's a very challenging problem. I actually think the interesting question is, can we find things in the middle ground here, right, where we're trying to think about ways to do small physical systems that are well protected. This is something that I worked on my thesis a long time ago. It was before even the universe was created, as far as I remember. And in particular, there was this model that I worked on called the quantum compass model, and we were trying to understand if it had these error-correcting properties. So the other day, I was working on trying to do simulations of quantum systems and trying to think about NISQ algorithms. And so, of course, all I know is stuff in my thesis, so I was like, oh, I'll try to simulate this thing, right, and do a variational quantum algorithm for it. So the interesting thing about this compass model, so you have XX interactions in one direction along the links and ZZ along the other direction, is that there is a code in this system, right? There are 4 commuting observables on these 9 qubits, and there are 2 logical qubits, which cannot be made up as any product of these XX and ZZ, these gauge terms. So if you're doing let's say I wanted to prepare the ground state of this because I wanted to know, say, the energy gap, or I wanted to understand dynamics on this system. How would I do that? Well, I'd just pull out my variational quantum algorithm, prepare my state, and maybe do an adiabatic ansatz, right? Alternating these XX and ZZs in a particular way. And I'll do a variational algorithm, so I hopefully get there faster than just doing the adiabatic algorithm, because the variational algorithm will find the proper angles to do this. Now, the interesting thing about this is if you do that, you say, well, what are you doing? You're running this experiment, you're making a measurement. What are you measuring? You need to measure these ZZ terms and these XX terms, right, and sum them all up, right? So you measure these expectation values to calculate the energy, and then you're going to use your outer loop, your optimization algorithm, to find the proper experiment. So what you end up doing, right, is you run a bunch of experiments where you measure in the Z basis and calculate these ZZ terms. You run it in a different thing where in the end you rotate and measure in the X basis, and so then you measure the XX terms. Great, you do that. But what's cool is that if you do that, you actually get error correction for free, right? Because those XX terms that I measured are exactly the products of them. I'm measuring everything in the X basis. Those stabilizer operators are actually what I need to measure to do error correction. So that quantum subspace expansion that was expensive and we had to do this extra thing, for this system that has an error correcting code in it, you're not doing anything extra, you're just doing extra computational work. And so I think this is kind of a neat bacon bit. It's not a shatter the world inspiration, but I think it's a neat thing that some systems appear to be better suited for like having sort of error correction when you're doing variational algorithms on them. And I think it does lead to a question that's been around for a long time. The first place I was aware of it that it was sort of talked about in any sort of more than just talked about, but sort of tried to flesh it out was this paper by Seth Lloyd, Ben Ron, and Charlie Ahn. And it's this question of if you have these systems like the ones that Microsoft is trying to build, are they easier to simulate because they have error correction sort of in them? And in particular, there's this sort of interesting space where we can think about, can we engineer systems, if we're trying to work in this intermediate space, can we engineer systems that are more robust to errors? And the reason we might be able to simulate them better is because they sort of have error correcting codes in them. And I think that's like a fascinating question that I hope somebody in this audience takes up the challenge and tries to understand. Okay, so just in summary, these 2 papers are on the archive. Everything I said that was wrong about them is my fault. And this is a recent picture of our group at Google, and I'm particularly excited about the near-term applications of this. I will eventually be able to simulate my thesis model, the model that I worked on a quantum computer at Google. That'll be pretty cool. If we get to a quantum winner, I'll go back and do software engineering, but I'm optimistic that we will be like this. We will be in the summer. So thank you very much.
Thanks, Dave. So do we have some questions?
I can speak up. So for the fermionic simulation, you mentioned that it simplifies these tunneling terms for the fermions.
Yeah.
What happens for the Coulomb terms? For the
So for the cool up terms, like the on-site in type interactions, I mean, what ends up happening is that you get a distribution of, if I go back to the slide, because I skipped over it pretty quick. You do get a distribution of the different terms, right? So the occupation one, right, ends up being slightly better. Like the ZZ term is always 3 Zs. It's those other hopping terms which can be up to 6 when you put them together that you get the bigger ones. So I actually don't think like this makes a huge difference. They're all kind of big and poopy. But there is some advantage for this. The biggest thing is that there is a distance 3. And also, just to be clear, this is also only on the square lattice. I don't know how this generalizes to other lattices at all. And you see the stabilizer also has this, I mean, if you go back and look at those stabilizers, they can be rather large, right? There's one of them that's 10, I believe, right? Yeah, there's a gigantic one, so.
Are there other questions? Okay, well, if not, let's thank Dave again. And then I think we have some announcements.
Yeah, so just a few announcements. So first of all, sorry about all the audio issues. We're trying to sort that out. Also, the poster boards are now up, so feel free to put up your posters. Some of them are kind of, behind columns and all over this area on the outside. There's 56 total posters, so make sure you have yours up and that you look at all of them. Also, right now, we're going to do the group photo outside on the lawn just behind you. So if you go out into the coffee break area, you'll be sort of guided out to where you're supposed to be. The setup will be in the lawn, facing the building, so kind of looking back towards the auditorium. The picture will be taken from the roof. Thanks.